All right. How's that? I checked out my YouTube before, but I did not check my video levels. I should have done that. Sorry for that. Okay, so what are we doing? We're picking up where we left off. It's actually probably a good thing. I'm like right on there where we left off. So there's another video. Go back and watch it. It's 2.5 hours if you want. You can fast forward it. And it goes through what I will summarize now in like 3 minutes. It goes through why I'm doing what I'm doing. I'm trying to make a rooted node tree so that I can create an abstract syntax tree so that I can take command box doc and any kind of language that I want to parse and turn it into an abstract syntax tree, which can then be used to rewrite that thing as something else. So that's what we're doing. The reason, you're gonna probably have to go watch the video to get an understanding of why I would want to do this, but it's a really valuable Go project. This actually doesn't assume you know any Go from the start, and as I'm showing you how to make a Go repo and everything, but I'm doing it for something that I need, and also something that's valuable that applies to computer science a little bit. Node trees are really, really important, and this is one of the ways to really learn it. So if anything's wrong with the video or the audio or anything, please let me know right away so that I can keep doing it. But I'm going to go ahead and go start. So when we left off, we had decided. So we go back to our example here. So we're writing these examples that become part of the documentation in Go. It's really great. And then we get these things. How is a developer going to use this? Because what we're making is for developers, not for an end user. Thank you. We're making something that's for a developer who might want to make a tree of some kind for any reason. There's so many different reasons to make a tree in coding. But the primary reasons that I am involved with are usually related to parsing, language. Another reason would be maybe a mind map. Maybe you wanted to make a Zettelkasten registry. There's all kinds of really, great reasons to do this kind of data structure. So the first thing is we want to say I want to create a new root node. Okay, so tree.new makes a new root one, and we can print it and it shows that it's a node. So that's the very entry level. How do I get a new tree? And really what a tree is a node, right? So at the top level, there's no encapsulation of the whole entire tree here. Some people do that, but we're not. The tree itself, so any node itself in the path here, any of them can serve as a tree, as a rooted node tree itself, right? And so the idea of having a node and a tree separate is kind of, it's sort of a mistake. It's not really accurate because any of the nodes is a tree. So we decided to make an alias, which is, it's not really an alias. It's just a method that calls a function that calls another method. And it says, so we can do that. The second one we did really quickly was we want to say new node. Okay, so tree.new node. It's like, oh, okay, I've got a new standalone node, right? And I can put that node anywhere in the tree. I can add it as a child. I can make it a new root and all that stuff, right? So that language, new node and new are exactly the same. They do the same exact thing. They just return a new node. But we kept it like that so that they could, word it that way. And that's where we left off. And then that led us off on the next question. Well, what is a node and what are its relationships, and how much of those relationships do I need to expose to my developer as opposed to hide from them and just do the right thing my way, in whatever way I can deem most efficient, without locking me into doing it that way every time. And that's what interfaces are for. And that led us to a conversation about interfaces. So this is an example. This is what we started out with. We started out with a node, right? And in order to even be able to do any sort of traversing of this, we have to have this idea of a structure. Now I've simplified all the names and stuff. I'm going to simplify them even more, but we've simplified all the names. But we started out by saying we have what did I say? I actually even updated the names. I want to change them right now. So what do we really want to do? Let's go back to what the user is going to want, right? And let's actually write those test cases right now. So I started writing the test cases, and then I realized, well, we should probably just write the interface for this. And then I kind of broke the interfaces all up into different individual ones. I'm going to undo that for now. And I have mixed feelings about doing this. So this breaking up the interface is like this makes it so that people can implement a certain interface without having to implement the entire node interface. But to tell you the truth, I don't really have a need for that yet in here, and it's really common for developers to over abstract things too early in the process. So I'm going to get rid of that. I'm going to go back to what we had before, and just decide, well, how much are we going to give people access to something? So I'm going to do this whole thing over again from scratch. I already rethought the whole thing. So what do we want to have users doing? Okay, well, we already know that they're going to have new, right? But new is not part of the interface for a node. A node is a node. New is already implemented in new node, and we've tested that through examples. That's not an interface, right? We already talked about wanting to be able to return all the children. And so let's go back to that. So what else do we want people to be able to do? Well, first of all, we want them to be able to get, so if they make a new node, this is something that changed, by the way. If they make a new node, we want them to set the kind of the node it is, which is kind of like a type. It's an integer that says, hey, this is what kind it is. And then we want to be able to set any value they want. And we want that, so I think we've already tested that, but we might need to adopt, yeah, we do. We need to do that. So these actually won't run right now because I changed the number of arguments. So let's do first things first. We'll go back and make our initial examples work. And then we'll jump into the interface of the node itself. In other words, what are its methods when we go from there. So I'm trying to, okay, so let's do, we need to pass it something. So we're going to say new. So we can say it's a new one, and if we have a new tree, you know what we could do? We could make new so that it doesn't take any variables, and it only gives you a root. That's interesting. Let's do that. And then it makes the root node, and the root node would always have type 1, and the type 1 is whatever type you decide to put on it. That's like the containing node for everything else. We can make it type 0. Let's do that. Let's do it as type 0. Yeah, let's do that. So then we can make that as type 0, and then its value, the value of root is always going to be empty. Yeah, I like this. Okay, so it's still a tree node, but it's just an empty tree node, right? Let's do that. Yeah. And then this way we can see this. We can say, like const, we could say enum or something like that, right? So we can say constant for, I don't know, top equals, or you could say element, I guess. Element equals 1. So we could have, you could even do, I don't know if you want to have it be all caps, it's up to you. So it's a new element node. I don't know, element, and then it has to have a value. And so that element is going to have to be, I mean, the value is going to be, like, it can either be something, we're going to put it just as a 0 element value. Now, the problem with this that we've had in the past is we weren't allowing people to change the value when they made a new node. And I actually think that we're probably going to want to let them change that value. Yeah. I think we need to do, I don't know, what do you think? We could do element, I mean, we could have, I don't know, we could do it like this, and then we could just say node dot value. We could say set value, right? Yeah, or we could say value equals. You know what we could do? We could expose the value and export that. Let's do that. That is what we want. Let's expose the value. We're not going to expose the kind though. We're never going to let. Now let's expose the kind. Let's expose the kind as well. I like this. Okay, so we're going to do that. That's a good idea. Okay, so new, writing new node, 0, comma, blank. So yeah, and it's a blank string. We could make it a blank string, or we could make it a nil. We could do a nil. Let's do nil. All right. So, well, actually, we don't even really need that. If we, yeah, I mean, this is barely more than would be done if I just did a return just a new, because these are the zero values. So this is what they're already set to, the initial zero values. So I could do this. I could do return new. I could just return a new node and be done with it. And that's fine. So 0 nil. Yep. All right. So, and then here, let's see our testing, see if it's working. So that gives us a new root node, or a new empty node, whatever you want to call it. And this gives us a new node that we can set the value on. I know I'm having second thoughts here. I mean, you're gonna watch me change the line mine a lot during this whole process, and you get to see the live process, and that's just the way it is. So I'm actually gonna expose kind and value, drop new, and just give it new node, and that's call it a day. And I'm actually also going to, we could make this variadic. If we could make this variadic, and I'm thinking of maybe doing that. I don't know if, I don't want to, I mean, it seems like that, I don't know how slow that would make things. That would make slow stuff down a little bit. I don't know what's going to be faster if you just make it like this, or, you know what I mean? You know, there's another part of me though that's like, I don't know. I feel like we're hitting on a kind of a happy medium that doesn't need any of this crap. Because what I could do instead is say, I could make this public, but then I can't use my interface. Okay, never mind. If I do that, I'm going to lose the interface ability. And we definitely have to have the interface. So I can't do that. All right. So we do need a new. So tree dot new node. New node returns a struct that fulfills the node interface. And we are actually telling it what kind of values we want here. And I don't know. This is a designer question. That's why I'm having such trouble. I don't know if I want to force people to put element / value here, or if I want to just do new node and then have them do node dot type kind equals. I don't like it when people put a lot of stuff in line. I like it when they write it like this because it's nice and easy to read. So I'm not going to even allow passing anything here, and that means that if I do it that way, it's not as efficient. I don't know. What do you think? This is a real trade-off, because if I do it like this, it's a little bit unclear to read, but it's fast to code. Do you think we should get rid of it? What do you vote, guys? I mean, I like the cleaner interface, even at the expense of performance. And if you know what I'm saying. So in which case too, we can just do this. We can just return new node. And you're going to see me write a whole bunch of code and just delete it. It's a regular part of development. And if you don't have the courage to do that because you've sunk cost fallacy, get over it, because you're going to end up putting stuff in your final code base that does not deserve to be there. But you were able to think through it by adding it. So have the courage to do that. We're going to say this. So instead of having set value here, because I expose those fields, I can actually do this now, which is nice. I can say, I have a new node and I want the node.type kind, the node.kind to be 2, right? And then I want the node.value to be something, all right? And because I exposed those fields directly, I can very efficiently set them. And by the way, those are safe for concurrency too, anytime you're setting a value, unlike a map or something. Maps are not safe for concurrency. And so I like that. That's better than putting accessors, set get and all that jazz on there. I don't really need to do that because I'm not validating any of the values. I'm trusting the person to just enter the value, and that actually makes it more efficient. But all this parent first and stuff like that, we do need that, right? And this is actually not an uncommon way to do this. I'll put a blank line here, and then you'll have the internal stuff, and then you have the external stuff here, okay? So even though the struct itself is private, you can only get one by calling new node, right? Then we can have the other pretty stuff there. So I like that. It's easy to read. You say I want a new node, and this is what the node stuff is. And then what? So let's say if our test works. It probably doesn't because we messed with it. So new node does type node and return argument. So this is new node returns a node. Oh wait, so this should be node, sorry. And then that's going to be fine. Okay, so now we pass. So, but let's explore our examples a little bit here. So, we could do this. We could say this. We could say, so what's the type? And then we could say, what is the kind equals, well, I don't know, we can say this. We can say type, right? That's why I'm saying kind, by the way, because kind is kind. And then we're going to have the value, all right? So I'm really glad I got a chance to sit on this and just like, this is so much better than what I was probably thought I was going down. So we're going to do node. So we get the node, then we get the node.kind, and node.value. And that should print out all nicely. And it tells you some stuff here. And then this, however you want to cut and paste that needs to go into the test output here. So we're going to go ahead and just paste that and then comment it out. I have a filter for this, and then get rid of that, and we should pass that test. Okay. So that's kind of the way this is going. I really like that we did that. A little bit too long of a line for me, so I'm going to go put this here. Another way to do this would be to make this a little bit more readable is I could have done this. I could have done these backtick comments, which allow you to do other stuff in them. And they're kind of appropriate for this kind of stuff. So our test is going to fail for sure because it's not going to be, we'll put a comma there. And actually we could do that. I'm just trying to make it a little bit more readable. This is going into the documentation. This is a little bit tough though because of that stupid indentation. I don't know. It's not gonna work. This is just a problem with the testing suite, not a problem with my stuff. So I'm gonna go back to my normal one, and I'm just gonna have to put line returns here. I did completion on accident. I hate completion. I don't know where it came from. It's like built into my thing on accident, I think. So let's try that one. Got tree kind because I'm doing backticks now. That was a waste of time, but oh well. I learned something. I guess we can do this. How about this? We can do that. Is that This is an example. It's going in my documentation, so I care about what it looks like. All right, that's why I'm spending so much time on it. To me. All right, so we got the kind, we got the value. That's easier to read. All right, so that's good. And that's all we need now. We don't need that other one that we had. Now, let's start to think about, let's go move to the next step. Let's start to think about how they're going to use this thing. How are you going to add to it, right? So what are the common methods you're going to want on the thing to be able to use? So, and that's where the interface came from. We're going to leave children there. We're going to come back to that one. But right now, this is the only one officially that's in there. I'm going to comment this stuff out for now because even though we might use it, I want to keep my code clean. I don't like leaving code around that's not going to get used. Go's good at helping you with that, but it's not perfect. So unlike other languages don't care, right? So what is the interface going to be to this node object thingamabob, right? Well, we have the top level function that gives us a new node, and that's the main thing for now. We have a kind, we have a value, and so every node is going to have a value. Not all of them have to have a value, and we know that they're all going to have a parent, which is a link to something above it. They're going to have, actually, let's do one of these. Let's find one of these guys like in here, right? How about this one? So let's actually rename this the way we have it. So we have, we're going to say next. So I'm going to actually switch that arrow up. I think I can just do it over here. Yep. I don't want to, I mean, it's going to, you know what? It was faster. It's this, I'm just going to delete it. So let's do that. So we have last child and all this stuff. These are all going to be here, but we made this internal. So previous. So let's think in terms of this guy here. This is not a final diagram by any means. This is just me screwing around. So, what? Why are you there? Right. So previous. So this is the previous one. And I want it to seem like it's linear. This is the children. I'm sorry. The siblings are a linked list. Okay. So if you know what a linked list is, then that you know what I'm talking about, right? So this is our node, and its relation to the top is a parent. Okay, so I'm gonna start getting into terms of, I'm gonna start writing it in terms of like, you know, Go code. It's similar to C code in this regard too. C has similar syntax. Where the heck did that thing come from? All right, so let's do this again. Previous. I know it's going to take some time, but this might make it into the final stuff. So we have a link to the parent, and we have a link to the previous. That's what the star is about. The star says this is a reference to that. That means it's a memory address, and I'll show you what those look like. And then we have, do we need a list to all the children? So this is the thing we were talking about before. You don't need that. And I actually thought of another reason not to do this. The only thing you need is a link to the first child. So I'm going to say it could be child, it could be first child. You know what I mean? We're going to keep a link to the first, and I'm going to cheat here. I'm going to show you some stuff here, and we're going to keep a link to the last. Why do we need a link to the last? Well, the link is kind of a nice thing, but the reason you want a link to the last is so that you can jump to the end and add stuff if you get a lot of children, right? You don't want to have to iterate through all of them to get to the last one. And so this guy here, we're going to make it a last. All right. So that's what's up. And those are, by the way, is that linked in there again? Ungroup. Is it ungroup like this? I don't remember. I don't care. I'll just gonna take it out here. All right, so this is the last. We're gonna call it last child, and because this is all internal references, I can use the shorter names because it's fine, right? It's actually last child, but I'm not gonna write that because I don't want to write that 1,000 times or how many. So this is the first child. This is the last child, and then we have a link to the next sibling. and a link to the previous sibling, and then we have a link to the parent. All of those are atomic memory addresses. That means they're integers, or they're, integers. And they can be changed in a way that is totally safe for concurrency. If I were to try to keep a slice or an array somehow inside of the cache or the memory of this node, I would have to deal with locking and adding, removing to it, or doing like convoluted things where we pre-allocated a number of pointers, references, and use and like you would have to do in C. And we're not going to do that. The only thing we're going to do is we're just going to keep track of the references to the nodes at these different locations, and then we're going to write methods and such that do the things that are necessary to change up those links. So like if we delete this thing, what happens, right? And the other thing that's really great about this is that you can set the I'm getting ahead of myself, but you can have the methods delete themselves because they know about their relationship to everything around them, and they can do all of the work to fix all of the relationships, and then boof, they can just go out of existence on their own. And that's one of the things I really liked about this particular model, which I kind of got inspired by the ideas from the Introduction to Algorithms book. There was one Rooted Node Tree in here that has something similar to this. And so that's where it's drawing from. And okay, so we've got all of our links here. We have a link to the parent, a link to the first, last, previous, and this is all internal links to other structures that are going to implement the node interface. All right, so, and we don't care about their kind of value. That's kind of payload baggage that comes along with it. So we need to start thinking about how are people going to use this thing, okay? We don't need to have set kind or set value or get kind or get value anymore because we exposed those and exported them, which is probably the right thing to do there. But we do want to do stuff like add a new one, right? And the truth of the matter is, let's go back to our model. What functions do we really want to give the developer access to do here? So ultimately, they're going to want to walk the trees, and we know that. So I'm not going to get that's the ultimate end goal. But when they're building up the node tree itself, how are they going to build it? How are they going to build it? How are they going to add to it, right? Well, we definitely don't want them adding all of these references themselves because it's just too much work to get right. So let's say we start with a root. We have a root. What's the first thing we're going to want to do? We're going to want to add a child, right? Now we might want to add a node, and we might want to add a sibling. And by the way, if you do that, it's a linked list. Right? Now I put tree in the package name, but another reason this tree could just serve as a linked list. Yeah, you could cheat, and because a rooted node tree is sort of a collection of linked lists just organized in a particular way, because that's what we have. A linked list is no problem. So a linked list is this. This is a linked list right here. If you take all the other associations off, this is a linked list. So this thing knows about its next thing, and this thing knows about its previous, etc. So you can traverse any time during the list. And to remove something from the list, you just delete this thing, its reference point, make this reference point to the next one, this one point to the previous one, and you can remove things from the list without losing anything else. And then all you have to do is garbage collect whatever this node is, if you're doing it in C or something, but that all happens for automatically in Go, which Rust people love to bag on, but it's actually so does Python, so does every other modern language. Garbage collection is safe and it's good for you. You want it. Stop letting people tell you that it's bad. I'm just so tired of that. Okay, so we want to have, it's not even slow. I mean, if you can build an operating system based on a language that has garbage collection built in without tweaking the garbage collection at all, you might want to rethink your position on, oh yeah, garbage collection is bad. I'm so tired of hearing that. So we're going to go ahead and make the stuff to do these things. So the first thing we want to do is we want to be able to add a child, right? And I started out with some different names here, and I deleted a bunch of them. And I actually ultimately wanted to say, let's see, I have, what's the natural thing? Well, I mean, the natural thing would just be add child, right? And I had, at one point I had, what did I have? Oh, append new, prepend new, append, prepend, adopt. I have adopt too. We're going to use adopt. I'll do that a little bit later. So we could actually get away with this. What if we did new? Right? What if we did new? If we do new, then what does new do? New returns a node. Okay. That gives us a new child. I could say new child. I could say add child, but we're going to say new child. So a new, I'm afraid people are going to think that that means to make a new node. Oh, thanks, Armand. I'm afraid people are going to think that doing new node here. So, I mean, let's be explicit here. Let's say a new child. Okay. Now we could say add child. We could say append child, right? I want to be careful with append and prepend though, because I want to save those for the siblings. All right. So we're gonna do that. So let's say new child. Some people say insert last child. Well, there's lots of other things, but let's just say new child. So if I do new child, I get a new node, and it adds. So not only that, but it makes a new node, right? And it puts that child there. And I'm glad we made the decision down here to not to not do our stuff to force the kind of value to be set, because now I can just do new child without having to force it to have a parameter signature every time, right? So now we have a new child, and then what? Then we can have besides new child, we can have well, we want to be able to delete ourselves, all right? So we want to be able to do that, and we're not going to return any errors or anything. We're just going to delete. We're just going to assume it can be done. I mean, there's really no reason to expect that any of this would not go away. I mean, the only way that would not work is if somebody did some really crazy, stupid stuff with the value, right? If they put a value in there, and if you wanted to let them delete, but to have it, like lock down a value because it's pointing to something else that it shouldn't have a business pointing to, and then delete it and all that stuff. That there's no reason that, I don't know. I mean, part of me is like, we should do this, right? So to do the go thing would be to like return errors on everything, right? I want a new child, and my new child is going to give me, it's going to return a reference to the node, and it fulfills it, and it's going to give an error, or an error if there is an error. If there's an error, it's not an error. I do not anticipate there to be errors here. If there are, then you're using the wrong interface. I just don't feel like there's going to, I think errors weighs the interface down too much. So I'm not going to do it for this. Seriously, if you are using values that are not just strings or something like that are like complicated and could cause an issue that you'd have to return an error on, then that's your problem. That's not on the interface. We don't want the interface to be, want it to be simple and fast and mostly dealing with data, and have it be very non-complicated. For a long time, I forced this to be a string, which makes it even simpler, and we really don't have errors, right? And atomic, right? So we have new child and we have delete. Now delete is delete self. So this is like delete self. It's going to show up as node.delete, right? So this is going to be node.new child, and that's going to make a new child. At one point I had spawn. Should we use spawn? What do you think of that? Should we use spawn? Spawn a child. We could use spawn. We could say new child. We could say new baby. I don't know. There's just so many things you could do, and stuff like that. I mean, there's just so many options there. So let's go ahead and put new child and a delete there, and we have kind here. And what else do we have? So now we need to start thinking about the siblings, right? And when you add a new child, what is it going to do? It's going to add a new child and put it at the end of all the children. And, if you want to change the children's up in the order, it's not going to be up to the node to do that. It's going to be up to you finding the child and then going through it. Which reminds me, we probably want to have a children. Okay. So a children is going to return all of that. It's going to walk the tree and give us all the children. right? But we're going to make it an interface instead of a struct because we don't want to part of the struct because we don't want to have to update it every time. That's the whole point. So this is a call. It's going to give us all the nodes at that moment in time. So, there might be a lot of stuff removed during that time, and there's no updating that has to happen here. It just happens automatically. Next time you call children, you get the right number of children that are there. So we have a new child and a children, and then we have the siblings. So, so we could say destroy here too. You could say node.destroy. Should we do that? Destroy. It's really what it is. It's like, this is, how would you destroy your node? Well, all right. I mean, it's really what it is. I don't know. Should we have destroy, node.destroy? I mean, we could delete, destroy. What do you think? What do you think, Stephen? So we have destroy. I can't decide. I mean, remove, right? Remove is another one. Remove is probably the appropriate one because we're removing the node from everything else. There's actually another thing called orphan. Yeah, let's say delete means I'm going to delete myself and I'm going to just go away. All right, so there's going to be some other fun things we can do here. We can actually do orphan. We can do emancipate, and all kind of thing. So, but we're going to do the next thing. So siblings. So I'm just going to put append new. Okay, and append new means I'm going to take a node as an argument, and that node is going to be added to the right. So back to our model. Append new, if I have a thing here and I call append new, it's going to stick one right in between here and the next one. That's what append does. And actually, if we do append new, it's going to make a new one. We want to have append as well, which means it takes an existing node and puts it over there. Now, there's nothing preventing you from taking a node that has already got associations with other things and then calling append on it, and that could get really convoluted really fast, right? But you can do that. You can do that if you want. So we could do that. So we have append and append new, and then we have prepend node and prepend new, and that will make a new one. All right. So we have children, we have siblings, and that's pretty much it. So, and then we have delete. So we need to have delete. We might need other stuff. We know we're going to need other stuff in the interface as we go. So, for example, if we don't have a need for it yet. So let's just stay with that for now. We're going to need some things like walk async. We're going to be able to look at once we allow people to pass functions that show how to walk the tree, we're going to need to give them access to look up the next and the previous and the children. Those things are going to need to start being looked at. We don't need to do it yet though. So this is just adding stuff on. So let's do that for now. Let's implement these first. Okay. And so let's actually write the code for those examples one at a time. And I'm going to yank this one. Let's see if we can get this done. How much time we got? Oh, I got to take a break here. All right. So I'm going to take a 5-minute break, and then we're going to come back and we're going to start writing this code. All right. Now we know what we're going to be writing. So I'm actually going to turn off these, and we're going to do them one at a time. Because why? Because if I don't do that, I'll get my test will fail because it doesn't fulfill it. See? So we're going to go back to the examples, and we're going to do one each one at a time. And oops, we only did that. Sorry. So we need to start testing the methods now. So now the way to do that is we're going to put the name node here, and then the name of the method that we're going to be testing. So we're going to be testing the new child. And you could get away with that as just new. You could get away with that as new or add child, right? You could do new child, and I guess we could do add child, and then have it pass the node. We can do that. A new child and an add child. All right, so let's do new child first. All right, and then we'll do them one at a time. So new child, and so we need a new node for the tree. So we'll say we'll call that root, and I'm going to call this root here. we don't really need to do anything with kind and value at the moment. We can later. And we're going to come back to all this stuff here. So decide what that's going to be. And I'm going to put a to do here. And I'm going to take 5 and we'll be back and I'll do that. All right, take a break. All right, here we go. So, yeah, there's a great question about in YouTube about that. I'm gonna go ahead and answer it. So Steven's asking, is there an explanation of why we're doing an interface instead of a struct? Okay, so clearly we could have just used this struct and made it a capital N and put all these methods on it and called it a day. But there are lots of reasons not to do that. But the number one reason in this case not to do that is because I want other people to be able to implement their own internal node sort of infrastructure and architecture, so that when they do new child or add a child or append a child or something like that, I don't care how it works under the hood. I want to abstract that away. I just want a new node. I want a node tree, and I want to be able to add a new child. That's it. I really don't care about the details. And I want to allow the flexibility, but more importantly on Go, I want to be able to pass into different things a node. And any struct, I can have 10 different structs that all implement node differently. And as long as they implement the node interface, they can be passed to anything that takes a node as an argument. And that is the primary argument for interfaces in Go or any language. So that's why we're making it an interface. I did have a moment of pause when you asked the question about kind and value. Now, normally, if this interface currently doesn't say thou shalt have a kind and a value. Your node shall have a kind and a value. And I actually kind of like that. It's like you can have a node that doesn't have anything else. It doesn't have a kind or a value. It can just be a thing, right? And then you can decide what properties to expose in your node as long as you implement these methods. Okay. And that's super great, because that means if I wanted to add an entire, I could have individual nodes. This is actually kind of if I didn't want to do it this way by setting the kind as an integer and a value, I can actually define several structures which are different node types. And then they could all implement the node interface. And as long as they implement the node interface, it doesn't matter what the structure is under the hood. So I actually without really thinking about it, I've actually unlocked the ability for me to have different types of nodes, like actual different types. Like I could generate a bunch of actual different types, and then instead of having one type of node with a kind integer and a value, which is just easier to write, I could do that, and it would be fine as long as they all fulfilled the node interface. That's the super important part, and so that's why we do it that way. It's a little bit convoluted, but you won't really understand it probably until we get into the hassle of writing it. Writing the methods and actually using it to build it and stuff. But yeah. All right. So next thing we're going to do here, we're going to make a new one. So we're going to do root dot new child. And that'll give us a new child. And then we can actually, we can do, I'm trying to stay away from print formats and stuff like that for now. But we're gonna have to bite off on that pretty soon. So like right now, if I were to do, I don't know, I can't really even get to the child. I could get to the children. This is a hard one because I don't really have any. You know what? I think we're gonna have to kind of jump ahead. Clog my brain. Yeah. So we're gonna have to. I think we're gonna have to jump ahead to how we portray these things, how these things are drawn, so that I can start making some examples so we can see them and visualize them. And I find myself getting pulled into this all the time. I get pulled into how am I going to marshal the thing into a string and print it, so that I can make an example that makes sense and it's readable. Like this one, was kind of okay, right? But how can I make an example that shows what new child does? And particularly because I can't look up the child, right? Right now without having it be a bigger test. And that's fine too. So how can I keep this test small? And what I want to do is this. I want to be able to do root.print. And I want it to be able to print out its static form. The problem with this is that, and it's a huge problem. As soon as you start doing a root.print in here, if you do anything to the serialized output, you have to redo all of your tests. And so I feel like, I don't know. It's funny. You wouldn't think that marshaling a string and creating the string format would be the first thing that you would reach for. I mean, it would be like the last thing you would maybe want to get. But when you start making tests, you're like, no, I actually need that pretty early on. I need to be able to use that, and it needs to be really solid and thought through well, right? In fact, it probably should be this. And honestly, I think it's so important that it needs to be here. I think it needs to be an interface. In fact, I think it needs to be an interface before anything else. And I actually think string needs to be one of the demanded interfaces. And I know it's grown a little bit, but if you don't have these things, you don't have a reliable way to visualize them. And so, what does that look like? And all I can say is that my test case is going to, here's another question. Do we mandate how every node is displayed in string form? Probably not. I don't think we should force that. I think we should allow people to represent them however they want. I do think, though, that if that we should have a form that we agree upon so that can be viewed. And I'm thinking that's probably going to be JSON, right? So if I do a JSON, I'm going to get a string of JSON, of condensed JSON. And this says that if you make a node, you have to provide a way for it to be seen as JSON. Now, some people would say this has no business being in the node interface, and I would agree with that. That has nothing to do with being a node. That has to do with something else, right? That has to do with being able to be stringable in JSON or something. So it's a different interface. If it's an interface at all, right? I like this idea. So that means that node down here is going to implement the JSON interface. We could do Marshall JSON. There's already interfaces for this, but I kind of like this. It's just easier than Marshall and unmarshal JSON. If you want to just get to the value. I don't know. So do you think that goes down in here or not? Probably not. So, and I spend a lot of time. I mean, this is something people are going to use a lot. So, and myself included. So I want to get it right. We're going to have new child here. I think this means that we have something to hang off of our node that does not necessarily need to be in the interface. It doesn't need to be contractually guaranteed. How's it going, Nick? This doesn't need to be contractually guaranteed to be, in every node, right? So we're just going to say that our particular flavor of node is going to be giving up. It's going to need some way to represent itself. So, and I'm going to just say right now that my style of node is going. See, I'm thinking all the way ahead to documenting this thing. And when I say that new node returns a struct that fulfills the node interface, I want to say this. I want to say it fulfills the node and the JSON and stringer interfaces. Does that make sense? So to fulfill the stringer interface that fulfills the node and let's see, stringer. String and YAML dot marshaller unmarshaller interfaces. So it's really important to me to tell the people that are using this that they're getting a concrete struct out of it that fulfills multiple interfaces, so that it can be used in different ways. They won't know that off the top of their head, right? Because they would see like a stringer. They would see this. They would see like an N for node, and then we're gonna say so string, right? So this fulfills the stringer interface. So string fulfills the stringer, the FMT stringer interface, which is important because you can, anything the Go itself uses this as JSON. Okay. Let's see. I'm going to put as a JSON array, and we're going to say I'm going to say go see JSON. Okay, so that's a method. So I'm kind of getting ahead of myself here, but I know what I want to do. And I did this already the other day. I'm doing it over again. So right here, so now we say this is getting a bit harder to test because we're going to be testing it. Don't get me wrong. Oh, by the way, this has to be not a pointer. You can't fulfill it with a pointer. You can't have a pointer. It returns a string and stringed, right? And we're gonna do something here. We're gonna actually we're gonna do JSON Marshall here, and we're gonna get it all. Don't worry. But we're actually gonna do something different. We're not gonna do. See, if I can already do this. This is already JSON-able, right? And that's important that people understand that. So, in fact, you know what? Yeah. Interesting. Yeah, if I were actually to keep track of the children here, if I were to keep track of the children here as an array of nodes, automatically marshal that sucker, and I wouldn't have to do anything else. Yeah, I could get away with that, but that's bad because I'd have to modify this underlying node slice anytime I removed a child or anything. So I'm just thinking about how heavy that would be. It's not something I would ever do in C, but see, okay, so I happen to know that the slices live on top of memory for arrays that doesn't get messed up anyway that hard, right? So it would not be that big of an impact. It would leave memory around for sure, but it wouldn't be that big of an impact for me to get rid of those. But it definitely would leave memory taken. That would be a bigger memory hog, and I don't want to be a memory hog with nodes because I'm going to have really massive stuff loaded at some point. I'm going to be loading entire documents and things. So I don't want extra children lying around when I start to delete something. So no, I'm not doing that. But which means that I can't get away with the regular reflection of JSON parsing and marshalling, which is actually really slow. And we've rewritten our own JSON parsing here. So I'm really getting ahead of myself here, but where at some point we're going to need to just dive right into how we're going to represent this thing. And I don't know if now is the time to do that. It probably is. And this is all coming from the testing. This is all coming from the testing. Because why? Because I want to be able to say right early on, I want to be able to visualize this. Like, what does this root going to look like? And I've already done this with another project. So how do I test this? What is the output of a new child, right? You know, how do I count how many children I have, stuff like that? This is hard to test unless I wanted to create a representation of it. And in which case we would say, okay, I have a new node, and we need some form to print it. I mean, one thing that would come to mind is you could just do println, right? You can just print your root like that. And then this, if you do this, actually, let's do this right now. You'll see this will actually give us something to look at. Missing return ended function. Okay, let me fix that. So tree.go. Tree.go. Where is it? what line did it say it was on? Everyone. All right, so print line root, FMP println root. Missing return. What? Oh, duh. Yeah, we forgot this. Okay, so let's just return an empty string for now. Actually, we have to get rid of this because if we don't, when you do this, all right, let me show you what string marshalling does. All right. So string marshalling is a fundamental part of Go. It's built into everything. And our marshalling to a string, undefined, tree.node has no field or method new child. Oh, well, we need to do that first. So let's do that. Func. Give it a receiver n for node. And we do need a pointer on this because we're going to be adding it to itself. Otherwise, you don't need it. So new child. And we have no errors or anything. So and then return. I'll just put a little doc here. It says new child. Actually, so this is a dilemma too. Do you put a bunch of documentation here, or do you just say go look at the interface where we documented what new child should be for everybody? You know. So for right now, I'm just going to say new child fulfills the node interface to. Actually, we need to return one let's see, and we want to return a new node like this, right? It fills the node interface by returning returning a new node. C new node for see new node for more about the struct returned. Okay, so return structs pass interfaces. We're going to come up here and say new child. All right, so new child returns a node. Notice how up here I have it returns a node interface, and down here I'm returning a node struct pointer. That took me forever to understand. I still sometimes feel like I don't understand it, but it works this way. So the reason that you want to declare the interface is saying the interface is, you know, high level stuff. It's like new child will return something that fulfills at least the node interface. Now it can do a bunch of other stuff, and it does, right? It can do a bunch of other stuff. It can fulfill the string interface. It can be all kinds of other stuff, but it minimally has to fulfill the node interface. All right. Now, one of the biggest mistakes I made, and I've seen other beginners, but mostly me, have made is they return this. This will make your day bad. Why? Because when you return an interface, that means that the caller can only use the methods defined in the interface. Let me say that again, because this is one of the most important beginner mistakes I've ever seen when dealing with interfaces. They'll put an interface for node that returns a node, and it's all upper level stuff, right? That says the thing that comes out of this fulfills the node interface. Right? And so they'll translate that and they'll say that also means that my concrete struct that fulfills this interface should also return an interface. Obviously, I just said I was going to do that. But the fact of the matter is, and this is very counterintuitive, what's to me, is that you actually are never, ever going to, the first time I did this, I thought, well, this means that people are going to be, you know, locked into, how's it going? This means people are going to like be locked into using that particular they're going to not use the interface that way. You know, I want to force the people to only use it as interface. And in fact, you want to allow the stuff coming out of here to fulfill the interface, but to do lots of other stuff. You don't want to force them into using only this stuff from that interface. That defeats the whole purpose of interfaces in the first place. So again, the mantra for Go is accept interfaces return structs. Okay, or concrete, whatever you want to say. That's the way to go about it, because that gives you the flexibility when you're taking in things, and it gives you direct power when you're returning things. And so long as the thing that comes out of here fulfills the interface, you don't need to do it. But I would add to that when you're declaring an interface, don't shy away from having your interfaces declare a returning of an interface. A lot of times, because they're going to be particularly like this, and file info is a good example of that. We talked about that earlier tonight. So hopefully that will help. And then we come down here, we can do a new child. So I want a child. So first thing I need to do is make a new one. Now I'm going to go ahead and call new node, because I might want to put something in there later that has it in there. Now, I don't know. I guess we'll do new node like this. And new node. So now I have a new one. It's an indirection level, but it's okay, because if I'm going to change it, I can go ahead and just change this one. I'll have to change it both. So new node. And I mean, if I was really concerned with, like, speed here, no, because I might choose to initialize a node at some point, and I want to have it all pass through the same thing. So no, I'm going to just do new node here. New node. I mean, I could bypass that and get a little bit speed out of that, but I'm going to lose support. And then later on, I'll go to try to, change this thinking. I'm going to change it for everything, and then it wouldn't, right? So new node. So we'll do a new node and then return new node. And that's good right there. That fulfills it, but it hasn't made it. That's just makes one. That doesn't create a child. So how is it a child? Well, it's going to be a child because why? Because we're going to make it so the node dot. So this is the current node. We want to make it a child. So then we're going to say the first, since there is no child on here, probably. Actually, no, we don't know whether there's a child here or not. Oh, wow. Nice. Yeah, this is great. I'm glad you're happy. So let's go here. We're going to add. So what we're going to add here, I'm going to be up to a while tonight because I took a big old nap. So we're going to add this on this one here. We need to get to the last child. This is why we kept track of last, right? So the last child, we're going to say, is there a last child? We have to do a bunch of questions first. So first of all, do I have a last child? So if last does not equal nil, right? That means I have a child. If I don't have a last child, that means what? That means I don't have any children. So if last does not equal nil, then we're going to add it after last, right? So we're going to say, well, what's the last child period? And so we're going to add here, go back to our diagram. So last is here, right? So if I'm going to add a new child, so 1, 2, 3 children to this guy, right? If I want to add a new child over here, I have to go to the last child and say, okay, last child, do you have a right sibling? And if it's the last child, it shouldn't have that automatically. That should be guaranteed. And because this is all internal, I can trust that that's true. I don't have to go crazy, and check it all. Yeah. Yeah, really? Oh, wait, that's nice. I'm glad I helped you. So let's do this. So let's say this. I'm going to do last. So if last is not nil, then we'll assume that there's no right hand to the last, or no next to last. That's why it's last, right? And so we're going to say last dot next equals the new node. So now, as soon as we do that, we get a brand new circle over here, right? And now, whoops, we get a circle over here, and now this one is pointing over here to this guy. All right, I mean, you get the point. And so we're done. That's it. Actually, no, because we need to check. There's another case we need to check for, right? We need to check for the case of, well, if that's true, then just go ahead and do it, and then just return it. Return and then, and I like this idea. This like return and then we're done, right? And we can actually write that out, but that's pretty self-explanatory. But what else can we do? So if there was no last, if last is not defined, that means there's no children at all. Because if I've ever added anything, I've definitely made it made, if it has children at all, that means first and last is set, no matter what, right? So that means if I didn't have a last set, that I was all by myself and I had no children, right? So I would, you could say no children. So you could say has children already. If you want, you can get crazy with your stuff there. So if there are no children, then what? Then we're going to say, if there are no children, then that's easy. So I can say last, I can say n dot first equals nn and n dot last equals nn. And I can just return it. So if there are no children, we can go ahead and just do it. I could have done this the opposite way. I could have said, hey, if there's no children, then go ahead and edit. But so these are two paths through this code. The first one is I have children. The first one is I don't. Now I could have also done this as a switch statement. There's lots of different things we could have done here, but that's fine. In fact, let's make this. See if we can do it as a switch statement. So let's do a switch. Switches are fun, and then we'll just always return NN. All right. So this is kind of an if-else tree. So we can say case last. I love switch. I cannot tell you how much I love it. I am a big, huge fan of switch. Case last and the default is this. All right. So I mean, it looks kind of pretty, right? And the thing about this too is you can actually put comments out here. You can say, so no children. And then over here you can say, wait, down here you can just say no children. Actually, we could make this case, we could switch it up, because which one is the most common case? Is the most common case that they're going to have children? The most common case is it's going to have children. So if last equals nil, yeah, I think we talk about performance at this point, so I'm going back and forth here. So yes, so we could just put here, and then we say no children, right? Now this won't let me do this, unfortunately, because of the Go formatter, but it's kind of obvious here. And here's the other thing too. You could say has children. Yeah, I don't like the formatter on this either. So say has children, right? You could say no children. So case last equals nil, no children, or whatever. I mean, there's just lots of different ways to write it, but I really like switch. Switch makes it nice and easy to read. It's all going to get compiled, so it doesn't matter. It's really just whatever is easiest to read. So we could say, I wonder if we could, I don't know which one's going to be first. Yeah. So the default is that it's going to have children. Case last is not equal nil, it has children, then do it. Otherwise, make a new one. What do you think is easier to read? You guys have opinions? So either one of these will work. I don't know. I mean, I don't know. I don't know. I'm just playing here. So if last is not equal nil, then just do it and return it in. I mean, it's kind of the same way. This is really what I prefer. So a little bit shorter. We'll just keep it that. All right. So last does not equal nil. Set the last one to that. Now we actually forgot something here, right? I don't even know what that means. I don't want to talk about that, obviously. So you have a question about coding? All right, so here we go. We have so we have last.next, and that goes. We actually also need to set up what the previous is, and so we'll do that. We'll do last. So the one that was last is no longer last, right? So that means we have to change the parents last. So we want, so wait a second, if we go to n.last, so the n.last equals nil, then we're going to go n.last, and n.last equals next. So the last next equals this, and then what? And then we have to tell the parent, we have to say n.last equals nn now. I forgot about that part, right? Because why? Because this, we just added a new one over here. So this pointer over here is no longer accurate. We have to tell this pointer to go over to this guy instead of this other one, right? And so that's what we do. So that's what we're going to do. We got our tree working on, and this guy, so the first and last, we don't care. And that's just thing. So this works. Now let's print that thing. Now this is what I was trying to tell you about the output. So here we have, I need to set the Pomo start and put our S keys on. So here we have, this is what, when you print out a struct in Go, this is what you get. This means it's a pointer, and these are the values. So this is the kind, this is the value, which is nil, doesn't have anything in it. And these are the internal things that we kept. So we could go back here and say, so this one is, the first one is parent, first, last, previous, and next. But the reason I wanted to see it raw format before we go back is this here is an integer. This is a memory address. It's a pointer to memory, memory register. And this is another one, right? Now, here's something cool. These are the same. Now, you should never actually do comparisons between pointers like you do in C, but there's lots of reasons not to do that. But you can tell that they're the same thing because it's the same pointer. Setting a number is an atomic operation. That means you can change pointers. You can change what things are pointing to. You can change the values of an integer or a string, and know that those are atomic operations that are never ever going to create a race condition. It's one of the reasons that the Rust people will tell you that kind of thing is super dangerous and you shouldn't do it. And well, no, there's no race conditions there. Don't let them make you afraid. It's totally fine. There are other cases where, like anything with a map, even reading a map is not safe, and so you do need to set up a lock or a message tree or something like that. There's many ways to do concurrency, but the easiest is with a semaphore. So anyway, I just wanted to show you that that's what it looks like. Now, that is obviously not testable, right? So this is not testable. That is not testable. I can't say, I mean, I could write a really dumb test that says, does it have a value, right? But I really don't really want that. I want it to, I could do an equality check, which would also be sort of wrong to do. In fact, I don't think can you do quality comparisons and checks? I think you actually can. I don't think you're supposed to do that, but I could say, on the testing here, it's taking me way too long. I should just do it. Explaining it takes so long, people. So if I'm going to write a good test here, I could say that, I could say this. I could say, does the well, I don't actually know, because I don't have any visibility into the children at all. And maybe this is the first time to say, no, we need to provide some visibility into the children. So we need to have something like root dot like last child, right? And I don't know. I'm trying to decide if we need to expose this kind of stuff early or not. I don't think we need to. So this might not be an example test yet. This might call for an internal test. All right, so let's try that. Let's do an internal test. Let's do that. If we actually gave it a value, so the problem if we do a new child like this, we're going to be testing a lot of things. So like if I give root a value, right? If I say roots dot kind equals 1 and roots dot value dot value equals foo or something, then when it prints out, you're going to see something totally different now. You're going to see nothing, right? Because, well, first of all, we're not printing anything. And the new child that we just created, we can't do anything with it because, oh wait, it returned us a new child. That's right. I forgot. Yes, let's do this. Oh, I think we can do this. Okay, this is good. So then we do the child. Then we can do child dot kind equals to child dot value equals bar or something. And now we can actually do some testing here. I can actually even do this like this. And yeah, let's do that. So now we can do this. We can say down here, we can say fmt print f, and we can do some stuff. We can say I want, so let's do the types of both of them. So you can do type root. I mean, this is overkill, but whatever. And type child, %t. These are both going to be tree something, right? Zero argument cost. All right. So root and the child. Let's put these over here. Put this here and this here. And argument list, right? Because you always have to have an ending comma. So we have, they're both tree nodes, right? We really don't need that, but I mean, we could just say, I don't know, root and a child. I mean, fine. I'm going to do this instead. Yep. I am. Sue me. It's just easier to write and it looks prettier. And some of these particular tests that we're doing right here, I kind of want them to be pretty. At least at this point, I want them to be pretty. And what do we got here? This goes up here. Missing commas. We have a backtick there. Put a backtick here. And there we go. So that's going to print there. That's fine. So we got root and tree nodes. So they're both tree nodes, right? So we can do this. We can do root colon tree. I'm just going off the deep end here because I want you to see how to make a good example test. And then we'll do it the other way. Root child tree.node nodes tree.node and so then what? We've got this here. And we need to fix it. So this is going to be, now it's going to pass there. All right. So, but that's not really what we wanted, right? We got a tree node, but let's give it some more things here. So we want it to be, what is root's kind? So we'll put a V for the kind and a V for the value. We'll do that here as well. And V, and so we could say root comma root dot kind root dot value. There's easier ways, but we'll just stick with this for now. And child dot kind child. And you can just there's other ways to do testing that are more direct, but this is going to be very visual. And I don't want to spend too much time doing the TDD, but on this one, I guess I'm going to go for it. So there you can see it gives you everything. And so this now, the answer is 1 foo. Get rid of that comma and 2 bar. And you see it passes. Okay, so that's all well and good. That didn't really show, it did show you that it came up with a thing. Now, the unfortunate thing right now is we can't really check the children. If we're going to do new child, we should probably check children as well. And I don't know if I want to throw that in here just yet. Children is, well, I tell you what, let's just do a children. Let's do children right away. And then, I mean, the question is, do we want to have a test that tests two things, or do we want to have it be just testing the one thing? And we want to test high level functionality, right? And I might be able to get away with that by just saying, printing out the children here. I certainly have set this up already to get that test. And so I actually think I'm going to do that. Let's do that. So let's say, this is the first children. I don't know. I'm just kind of skeptical. No. I'm gonna do a separate one. A separate one for children. But we need to do children pretty soon here, because we actually need to do the printing pretty easily. But I don't know. I'm just trying to. This is actually really good for me, because this is forcing me to not think in finite terms about the specific concrete one that I'm working on. And I really love that. So it's going to take me a little longer to do it. Plus I'm talking through it with you guys. So that was really easy. We added a new child, right? So we're going to be doing this continually for all of the other stuff. So the next things we're going to do is, what's the next inner interface? So now we fulfill the new child interface. We're 100% tested. We're not just testing low-level functions, right? If we were doing that, we would be doing more low stuff, but we are testing the interface to make sure it's supported. And we have got new child. We need to test add child, right? So let's do that. Let's turn add child on. And this isn't too hard. So we have new child, right? So we can steal all of this and make it for add child. And we're going to do add child. Add child fulfills the node interface returning, adding the node interface by adding the specified node as a new child. See new node for more about the structure turn. There is no structure turn. See new node for more about how to create a node to be added. So they say great engineers write great docs, and I think you should write them. Sometimes it's good to help you kind of think through the problem too. So in this case, we're going to say add child instead of new child, which means we're going to take a node. So we're going to take a C, I guess, CH, and we'll call it a node. Actually, no. In this case, we're going to accept a node. Anything that fulfills the node interface, right? And we're going to add that. And so we can get rid of this. Now, all the other code is the same. So, I could actually do NN instead. Let's just change all the CCs to child like that. Actually, let's do this. Let's change all these NNs to child too. That's a good idea. That's a little bit better of an identifier. I'm going to get used to doing that. Right. So there we go. And then I can change this one. Oops. Change that one up as well. Other than that, it's exactly the same. In fact, all I really need to do up here, let's yank out the internals, shall we? So yank, wait. Yank, well, I already did it. So this actually gets really easy. Yeah, all we have to do is this now. So now we just return ch, we return n dot new node, right? And we do add dot new node. That's all. So we do n dot add node new node. The end. All right, so keep our code all nice and pretty. Wait, add child. Wait, do we want new? No, we want new, add child, right? Yeah. Add child. Okay. So, yeah, we're good to go. So ch then becomes all this other code stays the same. We should be. What did I change here? I broke something. Add child new node used as a value. Add child new node. Oh, right, because add. Oh no, we can't do this. It's like that, but it's not that bad. All right, so we can do new node. We need a new one. So ch equals n dot new node. And then, oh wait, I see what's going on. All right, so we can do that. We can do n dot add child new node, but then we have to return n. Yeah. No. That's absolutely wrong, Rob. Absolutely wrong. So stupid. I'm stupid tonight. I need to probably take a break. New node. Change, and we'll make this a ch. And so we're adding the child, and then we're returning the child, of course. We're returning the child, not the add child. The add child doesn't need to return anything, so that's good. That should help us. New node undefined. Oh right, new node is a brand new node, so that's not a. Can use ch type as type node and argument send child. I was afraid of this. This it's going to say because it doesn't fulfill the interface. Have new child node. Want new child node. Which one? Node does not implement node. Wrong type for the new child method. Yeah. See, I was afraid of this. I think we can still do it. Oh, no. Yeah, we wanted that. Yeah. I this might bite me in the butt later. I told you, I have a hard time identifying when to return an interface. If I do this, that's completely stupid, because that would mean anybody implementing this interface has to return one of my specific structures. So that's not it. I know that's not it. So I think I might be able to cast, well, this should actually get past the problem right now. Cannot use type node, type as type node in assignment. Node needs type assertion. Fine, we'll do a type assertion right now. So we're gonna say, so add child. I think add child is gonna have problems too, right? Add child. Let me see, 3. Add child. New child, right? No, add. We don't. Do we have add child yet? Have we decided? Is add child in here? Yeah, it is. Okay. So add child has to be a node. So that also has to be assigned into a thing. Now this is, yeah, I don't know, man. So if I have a new node here and I return, yeah, we definitely don't want that to be an interface. That one I know. So this thing, I think what we could do is we could force this. We can cast that, and I think that'll get past that problem. Can't use ch type node as type node in assignment. Use type assertion on line 41. So yeah, so down here, I mean, I think we can actually do this. Yeah, I think I can do that. Line 41, yep. So 41 is same thing. So CH is a node. That one should actually work. I actually think I can use an interface here. Yeah, but I don't want to. I don't want to. Cannot use CH type node as type node in assignment need type assertion line 41. I already did that though. New child, add child node. I think I don't know. Yep, I think this is going to be great. So 41 needs a type assertion as well. Oh wait, now it's a node. I wonder if I can do this. I'm going to try something new. I'm in an unspoken. I'm in crazy territory here. So if I do that, I don't think I need this. Yeah. And new child, I think, can go back to returning a node. I just, okay, here we go. Yeah, this is good. That's what we wanted. Yep. Okay. So far, so good. This is good. This is good. And, I think we have everything. Too many arguments. Line 43. That's just an easy thing. Yeah. Add child. We're not adding anything. Yep. We're just returning. And returning. So we're just returning early, and we totally passed. Yay! Whew. That made me feel much better. I made a mistake. So again, I'm glad I was able to keep returning structs. That worried me for a second. Okay, so that's definitely the way to go. Time for chatting with us. No, I'm not gonna be chatting today at all. I'm just working. I'm making a YouTube video. I won't be chatting until probably next Friday. So yeah, I'm happy you guys are going. Things are going good. So we have children here. Add child fulfills the node interface by adding a specific node as a new child, and then we see new node from our okay. So there we go. We've fulfilled the examples. We've got our new node working, and we need to do some of the other stuff. So that's all good. Now we should probably be able to start testing stuff by checking out what their parents are and stuff. And I know that. Okay, let me put it this way. Let's expose this stuff. Okay, let's expose it, but not in a way that can be changed. All right, so let's put that in the interface. And this is good because this will allow us to test stuff. And we can test equality and things like that. So to do that, we need to expose it. We need to open it up. And so we're going to say, I mean, I don't know. The problem with this is if I put it in the interface, everybody has to do this. And I don't know if I want to force everybody who's making a node to have to expose the internals of how they are using it. You know, because that would mean like a very specific type of tree that they're using. But I think it's fair to say that every node in our abstraction is always going to have a sibling, a child, you know, a first child, a last child, all of its children, and it's going to have, yeah. So I think exposing these qualities of a node when they're added is a part of a good public interface in this particular case. And particularly when we start walking, because when we start walking, they're going to have to make, you're going to have to make decisions based on the node's relations to the things around it. So it's going to have to say, is my parent this type? And if it is, then, you know, this is a syntax error. So the interface into the node idea has to be able to inspect and look at the things around it, which means it's okay for that stuff to be public. So again, I'm trying to be really careful, not exposing things that don't need to be public yet. But these things are not going to be settable by anything, right? So let's start ahead. Let's go ahead and top here. We're going to say, so every node has a potential parent, okay, and it's going to give you a node. A parent has a, I'm going to call it a next. It's this next door neighbor. It has a previous node. That's the one to its, you know, I can do left and right, but that's fine. We'll just do next and previous. It has a first child and a last child. And so we could say first child, we could say, I don't know, we could say, I like first because I don't, people are going to be writing these a lot and I don't want them to have to write a lot, right? So first and last child. And I could say first C or previous, next and previous node. So which is the next node in the list? So you could say, I could say next, I could say sibling next, next previous, first and last. I'm just going to call it that. Yeah. The first node. I mean, I don't know. First child, last child. Right. If I force children every time, it sounds like one directional only. It is though. So we could say sib previous, sib next. And people are going to be typing this a lot though. So child first can have siblings. Yeah, well, of course you can. But that's what this is. But it wasn't really obvious, so I think you're right. Child last. So we have child first, child last, sibling next, sibling previous, and you know what I'm saying? You can say sibling to the left or right or whatever. This seems like it's a good interface right here. What do you think, Codex? I think this is good here. I mean, I know what's going on here, and I can read it pretty easily. Yeah. I don't want to write sibling. If I have to type, that's just not, no. Previous and next, yeah. I don't know. I wish I could get away with just dropping all that. I think this is more easy to understand just right out of the gate, right? So let's go ahead and actually do all this. We're gonna our stuff's gonna bail. We haven't called any of this stuff yet, but we haven't been testing it yet. Actually, yeah, we've just been testing new children and stuff. We've been looking at their values. We haven't really tested whether it's a node or not, even though they do fulfill the node interface. All right, so new child, add child, append to the node. We could say insert after, but then it usually takes a target. I don't want to do that. Append and prepend. I don't know if I want to do append and prepend. Yeah, append and prepend. I mean, is this implied that that's a sibling? It's a position in the scheme around it. What? Oh, I know. I know. Oh, the parent is just a convenience. I know. I know. We added the parent as a convenience because if somebody wants to go up the tree from down here, they should be able to do that. I didn't have it in my initial one. It was out, but you definitely want to know who your parent is. So yeah, because I mean, I want them to be able to bypass. That's why we have last too. So child last is a way to go right to the last child instead of having to iterate through the whole children. Append new, prepend new. I don't think we need a bunch of these. I'm going to get rid of the new stuff and call it a day. So add child. We could say add sib. And if we have if we add sibling, it's going to add it right after wherever it is, right? And we can get rid of prepend. We can just do add child and add sibling. Because why? Because I can go to the previous child and say add child. Yeah. So, you know what I'm saying? In fact, I kind of want to get rid of new child too. I want to minimize this. I don't want to give people too many options. I want them to, you know, make a new one. So I want to add a child. That's a new node. So I'm going to add a child, or I'm going to add a sibling. Add sibling. Not too bad. I could just do add sib. I don't know. Add. Yeah. We do need the previous though. So we need the previous sibling, the next previous sibling, add sib, child first, child last, add child, add sib, and delete. You can do everything with this, you know. And then we're going to add, just for convenience, I thought about adding siblings, which is cool. So this returns a list of all the children. The idea of siblings is just kind of a shortcut. So if you want to look through all your siblings and see if there's anybody at that level, who is, you know, the same as you, I mean, we could do this. We could have siblings, and if we did siblings, it would give you all of the nodes. But we don't really need that because siblings is just the parent children. So you just go parent children and I'll give you all of them, including yourself, right? So that's really all we need there. And that's it. I mean, that's pretty much it for the whole interface. And then we can go ahead and add stuff to it. So now we need to start implementing it. But yeah. So we get a new node, a new child. I mean, we're just going to do add child and call it a day. Yeah, I'm not even going to do this. Add child. We could just do add. Then you don't know if it's a sibling or not. Right? So we have add child. All right. All right, time to implement this. Think I can implement it in 12 minutes? Probably could. Let's see if we can do it. As I want to be done for tonight, but I think we're going to be able to get it all in. All right, so one thing at a time. First, we have a new node. So that gives us a new node. We got that. Then what else do we have in our interface? We have a parent. So let's do all of those really quick. Actually, I could almost generate these. I could, but I'm not going to. I could do, man, I could almost generate these. In fact, I think I made a thing to do that. And then we can see what's wrong with it. There's nothing wrong, but yeah. Let's do siblings. Actually, I think I have a script that does this. I just don't remember it. Yeah, I definitely have a snippet for this. But by the time I get my snippet done, I might as well just do it. Yeah, I'm just gonna bail on the snippets because each one of these, I just need to make a function for it. See what I'm saying? So the parent is just an accessor. This is one case where parent just returns, and I'm going to return an actual node, and the node, so I can say, this is another thing I hate doing, fills the end. I mean, you have to have docs in it to get coverage, but otherwise I don't like it. It's like, go look at the interface. The what's the name? Anyway, so return. I mean, these are like super easy. So we're just gonna return n dot parent, and so give this a receiver node. Yep, there's parent, and I don't even think I'm going to document these because these are all private anyway. This one needs to be documented, but this one doesn't. In fact, I don't think I need this. I'm going to put this in the interface doc. Yep, because I guess where it goes better. We'll add that back later. Yeah, sometimes this stuff can get in the way of the documents down here, documentation down here sometimes. We'll get back to that later. All right, so what do we have? We have parents, sib previous sib next, so sib previous sib next, and then child first last, right? And child first last. And so we can go find the parent and change this to be sib first. No, sib previous. Oopsie. Sib next. Child first. Child next. Child last. And same over here. We just say previous next. Put these back up here. First, last. First and last. All right, so those are all good to go. And this is all the accessors. And then we need the children, which just iterates through them all. Let's go ahead and do it. Not a hard thing to do here. Go. Hi, Mohammed. So let's do func n node children returns an array of node pointers. So then we create one. So we're going to make a children's why not? What a dumb question. Why do you want to know that? Because I'm making a parser why would I do that in JavaScript? Why would anybody write anything in vanilla JavaScript? It blows my mind. All right, so ch equals, I say children, I guess we can say children. That's too long. So CHS equals, we need a rooted node pointers, so we can append to it for, then we just need an infinite loop. So I'm just going to infinite loop this, return CHS. How do you create a login form on your website and functional comments section? Good question. Ask somebody who cares. I'm writing something. I'm making a video right now. So if you want to make a login form on your website, maybe somebody there can can help you. Okay. If you want to do what's in the title and you have a question about that, fine. If you have a question about anything else, that's fine, but put an exclamation point in front of it so nobody sees it, or ask it in the Discord, but don't ask questions that aren't about the stream because it's stupid. Okay. So here we go. We're going to loop through. It's an infinite loop. We're just going to break out when we have everything. And the first thing we're going to say is first thing we need to do is get the first child. So, first of all, we'll say if there's not a first child, then we're going to actually eject this. So if first child equals nil. So if we don't have a first child, then we're done, right? There's no children. So we just return, and this is a question whether we want to return nil or not, right? We want to return a list of children that's an empty list, or not. So I think I'm going to go ahead and return nil. It's like, I don't got no children. So there. And that if we don't do that, we could say, if we actually return the empty list, then people can still iterate through it and without blowing up. So let's do that. That's a bit nicer. Okay. Yeah, let's do that because that's not a nil, right? That means you got to return a list of nodes. And so, yeah, that would be fulfillment of the interface. Let me make a note here and here too. So, children must return a slice of nodes, even if there are no children. So I got to put all this stuff in here, so it'll be in the docs later. If some people implement it, they get it right. So that's fine. Then we'll just return a CHS. So that means people can range over it without being afraid of blowing up because of a nil. It's totally fine. If you have questions, it's fine. Just stay on topic. All right. If index first is nil, then what? What are we going to do? So if we got this far, then we have a first. So the first thing to do is to add that, right? Equals nil. So otherwise, we're going to do this. We're going to say CHS, and we don't know in advance how many we have, so we're just going to go ahead and do append, which is a relatively recent addition I found out to all of this to go. It used to be you had to resize your slices and arrays and stuff. Don't have to do that anymore. It's a COBOL or Fortran, lol. So we're adding. So we just added first, so now we have that, right? So for as long as whatever the thing is has a thing. So let's do that. Let's do this. Let's say current equals n dot first. So as long as current dot next is as long as current dot next is not equal to nil, we're going to add it. So we just do this some more. All right. Actually, we can get that out of there and we can just put this here. A little bit of a problem here, but no, we'll see. Oh, append. There we go. Oh, it's not equal to nil. All right. Then what? And then, well, what is the next condition going to be? So we're then going to say current equals. No, we don't need anything else. That's it. Why are you mad? Oh, because I need this. All right. So I need that, but I don't need to do anything with it. So then, what is this all about? I don't know. Go read the about page and read the title. We're making a rooted node tree, and then we're already like 7 hours in. So if you want to catch up, go back up and watch the previous video and watch this video from the beginning. We're parsing. We're creating a node tree like this so that we can then use it for all kinds of things, mostly for parsing abstract syntax trees to convert languages between different formats. And so that's what's happening. For current equals end.first, end.current equals nil, we're actually going to go ahead and change the current to equal the next one. And then actually, no, let's do this. Let's do the current equals current dot next. So this is a nice way to iterate. This is when you're doing if statements, so you can say, when you're doing for loops, you can say initialization check. So init check change. So this is kind of going to go at the end. So we're going to do this, and then we're going to do check this as the condition to see, and then we're going to increment it. So we're going to reset the current to the next one, and then it will do the check again, right? But we're going to start out with end.first as being our first one. So, and this will not even happen even once unless there is a thing that's already there. And then that will return all of our children. Okay. So that looks like it implements children. Let's actually write an example test for children. I wasn't going to do it in this one, but I don't know. I don't like making tests cover two things at once. I mean, because then one test will fail or all of them will fail, the dependency. So let's actually make a new example check for our children really quick. We have to make tests for all of that stuff, but we're gonna check the whole interface, but we're doing children right now. And that went pretty quickly. So let's go ahead and test it while we got it in our minds. So func, you have to change the new child from test. Which one? You have to change the new child from the test. When to find current. Oopsie, I got problems there. Oh, new child. Right. Good point. So we have a new node, and we don't have a new child. Actually, we have add child, right? So we have add child, and then we're going to say tree.new node. No. Let's do this. This is much better. Much better. Tree. Oh God, this is good. I'm so glad we did this because it's going to make it so much easier. And then down here, and then down here we just have it all by itself, and we say root.add child. So much easier to read. I'm so glad we did that. Yep, there we go. So that should pass. We got problems with current, so let's go look at that. So current. Oh, we need to have this be initialized. End.first, and this is not going to be end.first anymore. This is going to be append current. So we're just going to append whatever the current one is, and that should be it. Make sure we've got tests going on. Pass. Okay, so let's go back to our examples. Make a new example test. So function example, and we're going to be testing the node interface for what are we testing? We're testing children. Right, so children is the function, and we're going to output something. Don't forget your colon. Everybody always does that. How's it going, Loki or Leo? Why don't you just open it to the window to the right and save you from going up and down all the time? Because that's stupid. Because that would have two edit file notations, and then I wouldn't have to do it. I don't need to go up and down all the time. And besides, I can do file searches. But yeah, you can. You have a lot of suggestions that I know are well intended, but no way. So we need to print out the children. So what are they going to be? We can put the count. Let's do the count of the children. So let's add like 3 children. How about that? Let's start with that. So let's do. So we need all this code up here first. So we're just going to grab that. Yeah, I can just yank, yap that. Come down here, put this here. We have a new thing, so we have a new root. It's kind of foo, whatever. And then what? Now we need to make a bunch of childrens. So actually we could do, we could actually do like 2 or 3 children. We could say for, I don't know. We could say, for, and I don't know. Let's just say I equals 1 to I is less than 3 I++, and save you. All right, so we can add a new one. So we could say root dot, we already tested add child up above, so that's kind of a problem. So add child, and we're going to add a tree dot new node. No, we got to make a new one. Child equals tree dot. I love this forcing me to do that. That's what I wanted. So, and then we'll put child here because I have to set its values independently, instead of all inlining it all. Like this isn't fucking Rust. So we could do child dot, kind equals 2, I guess. And the child dot value, we can make something that's an interface, so it can be anything. So we can make it the number. We can make it a number, it doesn't matter. I'm writing bash there. Child what the fuck? Equals I. Sound good? And then it's going to add all those children, and then we're going to print out the children. So we could say children equals root dot children, and that's going to give me all of that. And then I can do md.println length of children. We'll start there and see what happens, right? So we got 3, we got 1. Well, I must not have added them then. Add child. We got a new child every time. Let's try something else. Let's go ahead and just dump the and dump root and see what's in it. Yep. All right, so let's see that. So there you go. What is this last thing? So this is where I'm really missing visualization because I'm trying to guess what those last 2 fields are, right? So we have the kind, the value, and then this is the first child and the last child. So that is not a thing that's working. So I'm cheating here, but I'm going to do it anyway. First child first. All right, so we have a child first. Oh, it did it. You see it? So it's a 2, right, and a 1. So we could do file last, which should be a 2. Oh, actually, let's make it less than. Let's make it 0. How about that? 0 to 3. That'll give us 3. So we have 2, 2. Yep. And now we nothing. So this is we only have 2 children. So 0. So child 0, child 1, and child. Let's do 1, and then equals to 3. So that means 1, 2, 3. We should have 3 children, right? What? Right. It says I got 2 there. The length of the children. I feel like it should be more than that. What did I do wrong? What did we do wrong? Well, let's go add some debugging. So let's say, all right, so let's print the current one. Let's just put some stuff in here. Println current dot value. Yep. And I'm going to go run the test again. Oh boy. It's interesting. Why? What? Oh, wait a second. What's current dot next? Does not equal nil. Next, let's try this. Let's do just a regular dump current, and that's going to give us all of them as we go. So it just is 1 and 2. So that would imply that, wait, current equals not first. Current equals current dot next. Does that mean it's getting the first one? So did it work together with language parser? Yes. Yep. So we get, it's sort of working, but not fully. So we only have 2 children. Am I only adding 2 children? I'm just losing it. I think so. I'll get rid of this one. Get rid of this one. So from I is less than 3. So the first iteration should be 1. Should we have 1? And then 1, I is getting incremented. So yeah. And then we do 1. So the next one would be 2. So 2 is okay. It goes down and does 2. And then it should be 3. And it should do 3. It should actually do 3 children. So something's wrong with the other loop. So let's fix that loop. Something's wrong with this loop right here. I'm almost out of time. But this loop here is, it's not working because I don't think it actually, no, it's getting the first one, right? We saw that. It's getting the first one and it's getting the second one. It's missing the last one. So this part right here is somehow not right. So, oh, I know why. Yes. We still want it to add that one. Yeah. So when we add, you know what it is? I know what it is. It's because when we add, we did, oh, I totally know. We have a problem with add. Yeah. Here's why. Look, you see here, the left side is not being set. So it's only setting the right side. So there's a problem in our add. And frankly, we didn't test that really well. We didn't test add child really well. We tested it, but not like thoroughly. So add child has got a problem. Add child is not adding the thing to the left. And that's the problem. So okay. So when we add a child, if there was not a last, we can go ahead and set that. So we can set the node at last to, let's see. No, we don't need to do that. We could say, okay, so if the last is nil. Now this is if last is nil. First and last equal the same thing. They're equal the same. If last is not nil, then we need to set whatever the current last is. It's whatever the current last is, its next needs to be set to the CH. And the CH's, this is the problem. No, that's what was wrong. Yeah, I feel bad about that. I did that wrong. Okay, so the last, the child's previous actually needs to be set to n.last. There, that should fix it. That should definitely fix it. What's I missing? So the node's last is now, oh wait, and then we also have to say that the n.last equals the current thing. There we go, much better. So see, this has got, so this guy points to, well, we're still missing something there. So if we don't have one, the first equals the last. Okay, great. And if we do have a last, if last is not equal nil, then we take whatever the current last one was, set its next to the CH, set CH's previous to the last, and tell the parent that the new last is the new one. There's nobody else involved there. So that should be correct. I just don't know why this is pointing to 4. Yeah, I don't know. We'll have to see about that. So that's correct though. So that part is correct, pretty sure. Let's actually write a test for that first. Let's make a test for add first so we can really test that out good. Let's do that. So we already have an add child. This is like a minimal test. This is a test for new child, and we need to change this. This is like totally bark now. So this needs to be add child. So let's do that. So we have a new node. We have a new node here, and we do add child, and we get a child. So this is actually just one case, right? So, so we can do add child, no, children, and you have to do the lowercase one because it's an extra thing. It's a reflection thing. How's it going, Iman? So this should say, what's up, right? And, the root.add child. There's a part of me that wants to keep track of the length the kind of way that other people do. So Go internally keeps track of the length as an independent thing, so it doesn't have to count it every time. We're making it a rooted node tree in Go. So we could keep track of a counter in there. That might be nice because you could have like the length, you could have like how many nodes are in it or like how many siblings you have and stuff like that. But instead of having to go through the children thing and counting them every time, that would imply having a cache as well for the children, so you don't have to look them up every time. But I'm getting into optimizations that we don't need. So let's test this first of all. So this says it passes. It adds a child. So we have, so the output is we have a rooted node tree and 1 and 2. Now we need to check some things that we were not checking before. And so we're going to do that. So we're going to say, if we add a child, that means that let's print, I mean, we could put the parent, right? So the child's parent, we could put PV here. And we could like play with this stuff. I don't know. Let's like do stuff like this. And so the child then has a parent, so child parent, right? And we'll look up the parent. So, and who's the parent? So the parent should be, but we're going to look at the parent up, and we're actually going to look up the parent's value. So the parent value is going to be, it should be foo, right? And this parent value should be nil. So if I look up what the root dot parent dot value, that should be nil. And printf needs 7 args. Oh, right. So, oh, that's bad. Oh, that's because I called nil. I called this. You can't do that. Because there is no parent, right? So let's do that. That should actually be nil. Child parent should not be, though. No. This is a problem. So we are still missing code in there. Yep, of course we are. We forgot to tell the children who his parents is. Oh my God, I feel so stupid. Obviously, we need to do that. So that, just fix that. That's not going to blow up anymore. There we go. So the parent knows who his child is. That was just a convenience thing. We didn't really need that heavily, but so that looks like it's good to go. I think we're probably going to call it for tonight. I mean, this is all going fine. We just need to get more insight into. So I think add child. We need to do it so that it does a sibling, and if we have another child, let's do that. So let's do child and change it to other, and we'll say kind 3, and we'll call it other. And we're going to add that child too. Add child other. I could make add child a variadic, actually, if I wanted to. We could loop through that, make it a variadic, just so it's more convenient. You know, maybe like add children, but I mean, we'll just do it for each one. It's fine. And then what? And so if we have child, we have other here, and we put other here. Other. And so we're going to get new values there. So others parent is foo, but we don't have siblings, right? So let's do a sibling thing. So the same thing. This will make the test pass. Should anyway. Other wanted child. Wait, did I save it? Okay, there we go. Tree. Oh, because it's type 3, right? Yeah, I think I did type 3. Type 3, other foo, what am I missing? Oh. All right. And pass this. Let's add the siblings though. So root doesn't have any siblings, right? So it's going to be nil and nil. So root dot sib prev root dot sib next, right? That's going to be 2 nils, and this is going to be a bit different, right? So I wish we could make these smaller. I mean, it's taking up too much space. It is. So I'm going to get rid of it. Root can change to R. Root. This is in the tile. All right. So let's do child C. Oops, wrong one. And what else? We're gonna do other. I'm gonna say other, like that other here. Oh, there other. All right. So, and it's actually very idiomatic to use one-letter things when they're locally like this, because it's just less. C dot sib previous. This is why I was having previous before, because it kind of adds up, right? Sib next. Add the same thing here. Change the C's to O's. And we have for FD's 12 has 18 arguments. Well, okay. So we're going to add more here. Add V, and do the same there. Oops. And that was a little bit aggressive. That was aggressive. And should have, getting something close here. Aha. Oh, look, it's printing like the whole thing. Yeah, we don't want that. We want the value or something. Value. Yeah. And actually, some of these are going to be nil. All right. So so other should not have an X. That should be nil. So let's do this. So this one has, so bar has no previous siblings, so it should be nil. And, but its next sibling value should be, other, right? So other, its value should be other. And this guy should have a value of foo, right? Because foo, way down foo, bar. Because bar is its value, so that's its brother or whatever. But it does not have a next sibling because it's last, right? Yeah. So I mean, we could do helpers like is last and stuff like that. You know, we could actually add those pretty easily. But I don't know. I mean, I don't know how I feel about like helper routines, you know what I mean? So it's like, I mean, we could do that. We could say that. We could say is last, is first. I mean, what the hell? Might as well, right? So we could say is first, uh, um, is last child, is a first child. No, we don't know that because we don't know if it's got a parent. It's not a first child if it doesn't have a parent. So no. Get rid of other here. Actually, no, this should have been nil. All right. Go back to test. Pass. Yay. That's exactly what we wanted, right? So that's very nice. We got what we wanted. And I don't think I broke the test, did I? Nope, didn't. Okay. So that everything's working. I don't understand why we were having a problem there. So the guy in the middle, the child in the middle, we don't, the problem is we only have one child. Yeah, we need to add yet another. We need to add yet another child. We have to add add child, no children. All right, so that's working. We need like one more, right? So so other is in root still, no? I don't think so. Other, this is the parent. So that's the parent, right? This would be so much better when we have like visualization with JSON, which is so super easy to add, but it just takes time. I've already done it in the other one. I just need to move it over. So I don't know how, it gotta be insane to watch this much video, but if you do want to watch this much video and you want to learn how to do this stuff, go for it. People, I mean, this is the kind of thing you can watch while you're working on it on your own, and you can kind of get ideas from it and stuff. So I'm going to continue to do it, even though it's going to take time. I think working through projects like this is hands down the best way to learn. It's pair programming, basically. You're just helping me out and going through it as we go. Can't parent get a future new node? Yeah, it already did. So we have a new node here, tree new node. Add child. Now I could actually add another one just for grins, and if I do that, I should get, that should actually change everything. I just blew my test up on purpose, but you see that it's no longer nil now. It's actually got a value. And so yeah, if I want to do that, I have to do this. So I could do, well, I'm not going to do that. So this adds a child. We have one case that's not being addressed, and that is if I have, we have to add a third child. We just have to bite the bullet and do it. I don't want to do it, but whatever. So yeah, we need a third one because then we can test the one in the middle, right? So we could say last, I'll make you last. Its value is last, and we'll put him as number 4. I mean, yeah. So actually, these children could all be the same. Let's do that. Let's make those all the same types of children. They just have different values. Okay, I don't care. I mean, because honestly, that's not important. The type, that's a little bit misleading. I want these to be shown as they're all different. Thanks there. So this one is last, and we'll say, so last, No. All right, so this one actually is going to have a next sibling, and no, its next sibling is going to be last. This one is going to have a next sibling. There we go. So this one is going to, instead of it being nil now, it's this. Okay, so here's 2, 2, 2. With this. All right, so they're all tree nodes, and this one is value is last. Its parent is foo. It has, to the left is the value of other at the previous, and the next value is nil. But now this guy's next value is going to be last. Now, if this works, our test is complete. Ah, there's our panic. That's what we were looking for. Okay, so there's something missing there, because we're looking at a value that doesn't exist. So that's good. It's like we've got our connection that's missing, and we can go find it now because we know what we got a test case that catches it. So that means someplace in this add is screwing up when we have a middle thing. I do want to see. I'm almost positive that it's the sibling next dot value that's failing. Could be wrong on that, but oh wait, we didn't even add it. Duh. So let's add it. That's why I was blowing up. God, this might work actually. So our code's good. I mean, I extensively tested the code, and it's fine. So we've just really definitively proven that children are getting added just fine. So that's definitive proof right in front of our eyes. That means the problem is someplace else. So it's not really a problem, but we're just incrementally writing this up. So we have a child there. So this is golden. We don't even need to touch that. But this one is wrong. So children is not right. And let's see. Let's actually test that. So I'm really going to town on this one test here. Maybe I'm just going to keep this one and then make it my master test. I don't know. We'll see. So we're going to do add child. Do we have any other add child tests? No. Okay. I was going to make children separate, but I've already got all the work to add children here. I'm just going to use it. So we're going to say count number of children, and we'll say v. And then down here we can say, so I shouldn't be doing this, but because I'm testing a lot of things at once, but we can say root dot children, and we can get a length on that. Right? Oops, trailing comma. And so there we go. Undefined root. All right, it's R now. I forgot. And there we go. So the number of children 2 is what we got. And what did we see? This is what I don't understand. It still says there's only 2 children, and I think that there should be 3 children. 1, 2, 3. So that means we definitely have an error. Number of children 3. But I think it's a logic flaw in my fancy. Make sure that matches. So that should pass. No? That should pass. No? Number of children 2. Number of children 2. What's up with the... Oh, because I put print statements in the children call. That's right. Let me get rid of those. All right. So that should be a 100% pass. All right. So, but this, we don't want 2. We want 3. And so that's what we want. Okay. So this is definitely where the error is. Current equals n dot first. So we set the current node to the first node. So let's visualize it. So we take this current node and we say, what's its first node? Go here. And we set that to that. And then it says, and then we check to see if current.next does not equal nil. So does current.next equal nil? And the answer is no, because, we saw that. And we keep repeating as long as current equals current.next. So this is the increment. This is the change we're going to do. So we're actually going to replace current with a new one for the next iteration. And then that should be able to tell us if the next one is there. So this first time through, it should append this. And it should be doing this increment first. That shouldn't be happening until the end of the loop. So it should be saying add the first one. Now we know it's doing that because the first one was 1. It was type 1. We actually checked that. What's happening is the last one is not being added. And the reason for that is because you know why? Because its next equals nil, but we still need to add it. It's just the last one. So that's what's up. That's what's up. Okay, that makes a lot of sense. In which case, we need to go ahead and add current. And so we can do this. We can say var current equals interface or equals a node. And then we can increment through these. And then after the end of the whole thing, we can go ahead and add the last one anyway. Yeah. You know what? I think I found another way to do this. This is better. We can say current does not equal nil. Yeah. I think that just fixed it. Yep. Okay. Good to go. Because the current equals the first one, and while it's, when we set it to the next one, if that's nil, hey, we're done. So go ahead and add them. So children is golden. And this is a good time to take a break when everything's working. We almost have it all. We need to do some testing on all the other ones, but we actually have previous, and we tested all of that in our ad. We haven't tested child first and last, and we did check children though. And actually we could probably check, I can test all of these right here in this one test that we're doing. And actually, if I do that, I can make my example a little bit more fulfilling and just open it up. Instead of having it be add child, I can just have it test node, period. And then it will just be listed with the node. And watch. I watch easily all of it. So we're almost done. I want to test all the children's stuff. We're so stinking close. How are we? I'm going to take a break and come back. I'm going to finish. This is almost done. So, everything else is related to like printing everything, and that can be in a separate video. I want to get all of this interface finished. We're almost finished. So I'm going to take a 5-minute break. And I'll be right back. Do. back early. We're gonna knock this out. It's really the downhill slope here, and then we'll do increment. We'll do like marshalling and printing and all this stuff later. I'm kind of glad I waited on that because this is the real guts of it, and the other stuff's sort of bike shedding. So we're gonna go ahead and add testing for child first and child last into the other tests because it's already done. So I'm gonna go ahead and print. First child, and then we'll put V, and last child, V, and so then we just do this. We just do R dot child last first. I mean, this is not even a hard test. I can just add it here. R dot child last. And semicolon or the thing. So what should that be? It should be the first child's value should be bar, right? So child first dot value. Now if this blows up, that's not bad, right? It should not do that because it would be nil. I'm going to put the value there. So the first child is bar and the last child's value is last. Foo is the very first one. And let's check that we are slightly off. Oh, because I typed it wrong. Other than that, we got it. Last child is last. And we're passing. Okay, so that's 100% test coverage for everything from here on down. I test everything to add child. All we need now is we need to test siblings and delete. And this entire interface is tested 100%. That's super cool because we'll be done. And then we can actually figure out visualizations and stuff like that later. We aren't. Did we test? Yes, we did. Sibling next to child first. Yes, we did all that. We're not testing any of the sibling stuff, so that's what we have to do now. Actually, we didn't even test sibling previous to next. Or did we? We did. Yes. Okay, good. So add sib. Add sib. Add sib is all we're going to do. All right. So I could like really go crazy and then just do add sibling here. Let's add a sibling to other because it's in the middle. Now to do this properly, we would need to check adding a sibling. Well, wait a second. I just realized that a thing we have a problem with. We cannot add a new first child. Because if we don't, we're like if you have a child, you can't go to one left to it. So if you have a first child, how would you add a sibling to it? You can only add one after that. You can't. So we're gonna have to actually add another thing. Yeah, we're gonna have to add. Add. So add child. Give me a sec. I'm thinking here. Give me a sec. So if we have add child, it can always add new ones, right? And if you wanted to add a child, but you wanted to force the child to be the new first child, you could get the first child and then say add sibling before. But how are you seeing the siblings? Right. So siblings are these guys next to each other. So, I mean, most node trees do insert child before or insert after. That's what they do. They do insert before, insert after, that kind of thing. How do you see the sibling as an external connection, like a tree grows to that node? Yeah. So what we need to do is we need to add, if we had add sibling before, so here's we go. So here's the problem. Say we have this, right? And adding a child is fine. It just keeps adding it to the end. If I come to this guy and I say add sibling, it'll inject a sibling right here and fix these links so it fits. If I say add a sibling here, it will work. But if I want to add a sibling over here, if I want to add a node that is the new first node, how do I do it? You know, I can say, raiding with party of 11. Hey, Vic Fred. Thanks for the raid. So if I'm going to, how do I add a node over here? Right? Now, there's a lot of different ways to do this, but we're trying to find a good abstraction for this so that people will understand it. And I think what the way to do that is to, because we already have first child, right? We already have first child and we have last child, and that's going to always be there. So we say, go to the first child and then add sibling before, right? So add sibling before this. And so we'd add sibling after, add sibling after, and add sibling before. Add sib previous to this, or before. Add sib before this. Add sib after this. I don't know if you want to say older or something like that, but you get my point, right? So we could just do add sib previous, and add sib. We're gonna have to do add sib. Add sib. What do I have it? Previous and next. Add sib. Add sib. No, we could say add before and add after. Yeah. Actually, no, we could do insert before. You want to have insert after or insert before? Adds a child of someone. Yeah. So insert before node. That's what we want. But the problem with that is that sometimes, I think that sometimes implies that it's a parent, and it's not. I don't want that to be a thing. Actually, no, I think we're going to do insert before. Insert before and insert after. Insert after. Insert this node. Insert this node after the current node. Insert this node before the current node in the children listing. So this is pretty common parlance for that. I think that's good. And if we had a child, it's just adding a new child, and that's nothing. It's actually the JavaScript for this is append child. That's what they say. Append child, insert before, insert after. I mean, it might not hurt to actually use that parlance. So I'm going to get rid of sibling previous and sibling next. I'm just going to use previous and next. So a node is automatically in a list, and I think that's important. So what is the previous node of this? Well, it's the up there. So what's its parent, right? That's going up. And next, I'm going to get rid of that. So child first. So yeah. Damn, I missed the stream. Well, it's going to be saved. So, so we have previous and next nodes. We have insert before and insert after, and we have child. So all the child stuff begins in the world's child. That's good. Append child. So, and there's like insert before. I think we want just append child. I know we want add child. Add child. Every time you add a child, it just adds a new child. It gets born to it, right? And then all the children. So do that. Add sib as a child of someone. Yes. After you will need insert after, right? Insert after a node and insert before a node. Previous next. So child first and last child. I think this is gonna work. We're gonna have to change some things because I just messed it up. But Yeah. Okay. So we got the parent. I'm going to just change this to previous. Next, I want the idea of a node for people to think that it's a member of a list, because it is. A node is already a member of a list, and that's like children in HTML or anything. So, and then the child first and last. I do want to put child in front of that so that people don't think it's the first in the list. It's like, no, this is my first child and this is my last child, right? My firstborn. Insert before. Now I have both. Insert before and after. So yeah, I think that's probably good. We'll keep that there. So child first, we're gonna have to repeat this. So child first is first, last, previous, next. Got that. I think we're good, and we can start implementing the other stuff. So, I mean, this is all doing internal stuff that just implements this stuff. So that's all good. Yeah. Our test blew up for sure because I changed some things. Subnext is undefined. We're gonna fix all that. So, yeah, we're gonna do some of this. New node. We got this. Add child. Wait, did I redo this? Oh no. Okay, here we go. Tree is a new node. Add child. We did that. We're gonna do. Did we do add child? We changed that. I can't remember. Add child, right? So we'll leave add child. Yeah. I mean, I like verbs, right? So, and this is what the problem is. Okay, so down here we have parent, which is the thing. We have previous, which is much better. And next, previous. Next. So any node can be used as a list. You can use nodes as a list, linked list. I like this because I can use this whole entire tree thing either as a linked list abstraction or as a node tree. If I want to use it, I can use it in either thing. This you get 2 for 1, and that's nice. All right, so what do we have here? We have linked list, linked previous value, child last. Probably need that. Child first, we need that. Children, is that pass? Let's check. Yep. All right. So new testing. So now we need to test. Actually, we don't need this anymore. This whole thing can go away. Yeah, we might get away with just the one test. Yep. And oh, man, we're almost done. All right. So first and last child we have, add child we have, children we have, previous and next we have, insert before, insert after, and delete we do not have. All right. So let's do insert before. Let's write the test for that. So let's take our current situation here and let's mess with it. So let's say we got all these children, right? And let's mess with it. So now we're going to actually do some inserting. So we're going to do r dot insert. No. We're going to do o dot insert before, right? And we're going to make a new node. Now you need to make a new node here. This is the really crazy thing with this is you can actually use other nodes that are already linked to other things and get really crazy results. Symlinks and stuff like that, right? But that's up to the author to do. A terminal and a vim tab. What are you talking about? No, this is tmux, Mohammed. Yep. After a while, and it's not a tree anymore. It becomes a matrix if you're writing search functions. Well, I'm not going to be writing a search function, but yeah, it's not a matrix. This is a rooted node tree, but I want it to be able to serve dual purposes, both as a linked list and as a rooted node tree. This is in Go, so it's in the title, but just in case you're looking. Yeah. So insert before, and so this is we want it to insert whatever is being passed. So we need a new one, right? So we could say, let's make another one. So let's say, actually, let's say we're going to say new first. Yeah, this is important. Actually, this is super important. We're testing this. So let's do that. So if we take the first node, which is what? So the first node added was C2 bar, right? So if we take the first node and we do the insert before that, we get a new first. So that's good. That's what we want, right? So we're gonna have we're gonna say first, and I don't know. So firsts, right? So I don't know. We could even do new firsts. How about that? A new first node. So new first, and new first equals tree dot new node. And I had a tree dot new. I could almost just do node dot new. I could do that. I could make. I don't know. I mean, it makes me wonder if I should rename the package to be node dash go. Everybody's gonna really wonder what that is. So we'll just keep this. I mean, I may end up abstracting different types of trees at some point and put them in here. So, and have helper functions and stuff. So I'll just leave it that way. So new first. So we have insert before new first. Now this should like blow everything up. All right. And yeah, so I kind of, I don't know what to do here. We could, this is really going to blow stuff up because actually, if we do this, we're not gonna be able to test the other stuff first. So we need to test that stuff first. Kind of feel like this needs to be a different test sort of. So this, we do all of this great printing here, and then we're gonna mess stuff up. Okay, so now we're gonna do, God, I almost want to make this like some sort of way to visualize the whole thing. This is where I really don't want it. I mean, I've got this big old printed visual thing, but I want to just be able to dump a JSON thing. But I don't want to inadvertently have to test all the JSON stuff as well. So insert before new first. If I do it here, it's not going to give a proper test everything else. So I have to change the state here. All right, so let's do that. And then actually, I don't even care. I'm going to take all of this code and put it here because I can. I don't care. All right, so new first. So now after this, what's going to change? So after we just did instead of new first, we need to give it some properties. So it doesn't have any properties at all. So new first. Let's make a new first here. This test I know is hairy, but then I don't have to write down one test. So, and it's an example, so everybody can look at it and like deconstruct it and see if it's working, how it works. So here we go. So we have the new first equals a new node, and we're gonna put new first dot. We're gonna go type equals 3 just because these are completely arbitrary. These are for the developer to set. And new first dot type equals new first. New first. I'm gonna say first. All right. So what does that do? Well, now we have the child and the other and the last, right? None of that changes. So I don't know. I don't know if we should do this as like this or not. I mean, we could, because then I have to like print all this printing stuff out as well again. I don't want to do that. It's just too much data in a single test. What do you think? It's just too much. I don't like it. I'm going to change it. I don't know how to do it. If I do, well, okay, fine. We will put this here. It's, unfortunately, we're going to lose some of our testing. Some of our testing is going to be lost because it's not going to be represented properly. But that's fine. So new first. So if we do insert before, C insert before new first, then the child parent value is the same. The C dot previous is now no longer nil, right? The C dot previous is now first. Yep. And dot value. We can refactor these tests if we need to. That's fine. And what? And the number is 4 now. So let's see. That should be it. Type has no filter method type. Oh, did I do type? Really? Don't know my own thing. This should have been kind, and this should have been a value. All right, so insert before undefined. All right, well, let's define it. We're gonna do now one. I'm almost done, I swear. Okay, so children, children, add child, insert before func, n node, insert before ch node. Actually, huh. Yeah. I think this is wrong. I think this is supposed to be this. Yeah, I don't know. I'm trying to define. Did I do that wrong? I think I did. It says parent undefined. Type node has no filter method parent, but does have parent. No, we are not doing that. Yeah. Yeah, I don't know. I feel like I'm missing something here. I feel like I should be having this accept a node. Yeah, I think I'm supposed to do that because right now yeah, I think that's a mistake. Right now, if I were to try to add a child that fulfilled the node interface, I couldn't because it would have to be a node. So this is actually not fulfilling the interface. No. So I need to make this a node. Yep, and that's going to force me to make a bunch of other changes. I'm glad I found that. See, but this, I was afraid of this. This is where you have to start putting accessor values and stuff and mutators. And I struggle with the interface part on this a lot because it doesn't create, it receives a node, it doesn't create it. Yeah, but okay, so a node is a fulfiller of the node interface. Does that make sense? So the only way for me to test it, you know what? I need to test that. We're not done testing add. You know why? Because yeah, I got to test this. This is something that it's been bothering me for a very, very long time. So I'm going to, okay, let's finish new first and then we'll do that. The reason we need to do this is we need to test what this looks like. I mean, so far all of this has been working, right? But what if I make another thing that fulfills the node interface? I think I'm okay, but you know what I'm saying? Because there's nothing that's here that says that there's nothing that's forcing it to be a node at all. There's actually, we're not using nodes at all. We're returning a struct and we're using that struct and we're fulfilling the interface, but we are not really using it in that way at all. So yeah. And so this right here, so add child, this should be failing right now. Make increments so that we can see depth in the test. Yeah, for sure. So for example, I want to get rid of this test for a second. I'm definitely going to get rid of that test. Yep, I'm going to change this back. So we change this to 3, and this should be nil now. Make sure the tests are back to normal. Nope. Yep. Yeah. Okay. So that test is good. In fact, I need to commit this. So add. Yeah. Commit. Was it all but add code for most of interface? I don't know. So I don't want, I mean, okay, so yeah, because I just don't want to lose it. Yeah. Anyway, yeah, I'm gonna tag. It's not finished yet, but I don't want to lose this. All right. So here's the problem here. So this is something that's been bothering me for a long time. What if we make a new node, right? Like we define a new node type. And I'm going to make an example of this. So let's say func example node, alien node. How about that? It's an alien node. So if I have an alien node, I should be able to use this entire interface, no problem. And if not, I've got problems, like big problems. So I don't care, whatever. So then we're going to say, we have to declare and define a new node. So we're going to have to say stuff like, I don't know if we can even do this within here. I guess we can. Well, actually, no, we're not going to be able to. We're going to have to, see, this is the thing. We're going to have to define all of node, everything. I mean, it doesn't have to work. It just has to fulfill the interface. So, yeah. No, this is, you know what? We have a problem here. I really think we do. I think we have a problem here because I think that this is supposed to be a node. And I think that that's what's supposed to be doing the filtering. And we haven't said anywhere that R is a node. You know what I mean? So this is returning a new node, but it's not passing it as a node. And maybe I don't know, maybe I'm overthinking. Again, we should have something be able to fulfill the interface and be able to be passed in. And so I'm gonna do that. Actually, I'm gonna do an interface test right now to learn this. I don't know if I have time for this, but I'm gonna do it anyway. It's kind of a different thing. Insert mode to give a human calculation. You can, but I don't like it. You definitely can. Yeah, Control X. Yep. You have to do it fast though. Yeah. I can't. Mine's not working. It has to be an insert mode too, right? Yeah, I think it is. If you're in insert mode and you're here, you can do XP. Yeah. Yeah. I think the X was the undo on mine. Anyway. So here, okay. I feel like I've got this down, but I don't feel as comfortable with it, and I want to give it a shot. So I'm gonna try something really quick. Get rid of this completely. I'm going to do kind of a learning lab. And this is going to, you guys, this is not going to go fast. So I'm going to, I really want to, I won't be able to sleep if I don't do this. Sorry. So I'm going to make a new set of Tmux windows for this. And I'm going to put a mark in the stream right here. In case somebody wants to like do a thing and skip it. But I'm gonna validate the use of interfaces properly in that at that point. I use interfaces all the time, but I constantly question myself when it comes to this kind of thing. So I'm gonna go back and verify that I'm doing it right. So I'm gonna make a lab, make directory lab, go interfaces, and this is going to just be all things about interfaces in it. And I'm just going to experiment. I've read a lot about it, so I can just experiment. And go init, get init, and go mod init. I don't really need to do any of that, but I'm going to do it anyway. Just because I don't want to deal with Go interfaces. And gh repo add create experimenting with Go interfaces. Make a thing there. Damn it. Make it public. It's fine. People want to see it. I don't care. And so then what? We're going to make a library. lib.go. That's not main, you stupid thing. We're going to call it, I guess it could be main. I don't care. And what the hell not? Okay, main.go. And so we're going to be printing stuff out here. That's fine. What the heck? I'll just put it here. So we're going to make an interface. So the first thing we're going to do is make an interface. So we have type let's call it printer. Why is Bash losing popularity to Z Shell? It's absolutely not. Who are you talking to? A bunch of Mac people? Okay. Why don't you talk to anybody in the world of professional containerized native applications and development? Or I don't know, like the industry standard for Unix shells. Z Shell, it's a false perception that Z Shell is because the people who like Z Shell love to talk and they don't like to do shit. They talk a lot about Z Shell, but they don't actually do anything significant for the world. There you go. You got my true opinion on that. Seriously, people who like obsess over picking Z Shell and fucking around with stuff that's not the default spend so much time ricing their systems that they don't actually do anything. Sorry, you can hate me, downvote me. I don't care. Z Shell is a bad idea. All right, I tried it. I used it for a full day. I did. I tried everything. I'm like, oh, this is like crazy. What? None of that is dangerous. But I'm not gonna talk about that anymore. All right. So type. We're gonna do an interface here, right? So let's do type foo. Now let's just really do this. We're gonna call it I don't know. Let's call it a printer. It's a printer. It just prints stuff. I don't know. I'm a fooer. I don't know what should I call it. Printer. Let's just call it printer. Interface. And it just prints stuff. That's it. So it has to have a print function. That's all. And that's it. But it actually, yeah. All right. So then we're gonna make a new thing. We'll say func new printer, right? And we're gonna actually make a printer. So struct printer. I'm gonna do my little thing that I do. well, I know I just lower the case and do it. And in here, we're going to have, I mean, we don't really have to have anything, but we could have buff, I guess, whatever. I don't care. Buff string, right? So, yeah, let's do that. Let's make it public. And so you can actually set it and everything. So a new printer, what does a new printer do? A new printer returns a brand new printer thing. Return a new printer. Okay, so printer, that's all well and good. And what else do we have? All right, so now we need to do, we actually don't need to, I mean, we'll just use this for our test code, but so if I were to say this, if I were to say, I have another thing that wants to implement a printer, right? So if I want to have another printer, so let's do that. So another printer, and we'll put that here. Okay, so with this original printer, it's title, and we have an original printer, and then we have another printer. They both fulfill the printer interface. And yeah, so we'll say new original, and we'll say a new another. So to yap there, and we'll say another, same sort of thing, I guess. We'll make this one, have it called buffer or something, because it's not part of the interface. And new another. So this gives us a new another. New another. And so we'll put main here. All right, and so there we have two different structs that are implementing the printer interface. Well, they should. They're not right now, right? So the first thing we need to do is have them have a receiver. So we're going to say that they're going to take a printer, p printer, and they need to have a print function. And all they do is they print their buffer, right? So fmt println and just print their buff. p dot buff, right? That's it. And we'll just print on it. I don't care. We'll put this also in the other printer, so it implements it as well. So the other one implements it. Another. And so now both of these are implementing printer. And this one has to do buffer. But again, the exported structure members are not a part of the interface. That's not the thing. They both have a print method. They both fulfill the printer interface. So then the third thing comes in is something that takes a printer, right? So then we need something like this. We need to define yet another thing. So it's something that uses a printer, right? So h title, and so then we have something that uses the printer. And so I don't know, we need something that takes a printer. We got just a plain old function, right? So we can have, the function could be, how about this, print with printer. And then we take a p, which is the printer. And then we have, a string with a buffer. I don't know. I mean, this is totally stupid, totally contrived, but it doesn't matter. And which P for printer, and then we have use printer. I guess we could do use. That's fine. Yeah. So we could say use printer, right? Or we could say dump printer or dump printer, right? Call it use. Yeah. What's that? So use this printer. In other words, I want to use a different printer. It's already been loaded up. We could say use it or do it or something like that, right? And that can return an error or whatever, but all we really want to do is call p.print, and it should already have the buffer, should be already filled up. So the printer itself could have a different buffer filled. So down here, let's do that. So let's do that. Let's say, so we're going to make a new printer. So I'm going to get a, so the P1 we'll say is a new printer. And is it original? A new original, right? Is a new original printer. And then we're going to, let's see, it basically sets the next step. Yeah. And then we're going to print it. Okay. So we have a P, I'll say a PO over that. And then we'll have a P, I don't know, original. And then what do we have? Another. Yeah. Okay. So we have another printer, a PO and a PA, a new, another, and then I can actually set the buffers. So the PO dot buff equals original buffer, and the buffer here is the PA's another buffer, and then I should be able to call them both, right? So where are we, by the way? CD ended. Well, I could just, I don't know, let's do that. Go interfaces. All right, so we do go run main, I guess. I don't even really need to do more than that. I kind of want to go test here because I can just rerun it. Watch, go run. All right, so that's fine for now. I don't care. Anyway, so what do we have here? We have a printer, and this is having trouble. I don't know why. Okay, they're not using anything. Wait, line 9's got a problem. What did I do up here? 8, 9, struct printer. Oh, type. Yeah. Type. So, all right, there we go. And we're not printing anything, so let's try that. So then we need to call it. So then we say use PO and use PA. And we should say original buffer and another buffer, right? So far, so good. I mean, that is a thing. Now, the problem we have is that we haven't defined another interface that returns an interface of that type, if that makes any sense. So I think this confirms that our interfaces are working, right? This accepted, but we put it in a function call, not in an interface. Now, if I were to add another interface that says, let's try this. This is like really crazy, right? So interface that depends on another interface, right? So this is a thing that we have, and this is the thing I've always wanted to know about. So I'm going to mess with this. Node in new node. It doesn't need initialization. It's got zero variables. Yep. Yeah, a new node is just a new brand new spanking new node. It's not being added. We use add child for that. Yeah. Yep. I mean, yeah. I'm just about ready to just hand over a node that's uninitialized at all. You don't really, I just like have the option of initializing later. So, okay, so we have another interface that depends on this interface. So let's say type usable. I'm just reaching here. Face is usable. So we have, it just has a use function. So we could say usable printer, right? So use is not a type. So we can say use, but it takes a printer type. See that? And now what? So it still works, but you know, it's we're not passing it, right? So we could do this. Let's say, I don't know, we could say uses printer, and we could say type, how's it going, Jonathan? So we could do, it's just, it has next and previous. Yeah. So here we go. So something that uses a printer. So let's do that. So let's say we have a struct, and use sets next and previous. I think so. So I don't know if we have a struct, we have this. I don't know if this is going to work. Thing. I could say a user. You could say we have a user, and the user is a struct, and type struct. Yeah, sorry. And so we give our user a printer, and I don't know what to tell it. I don't know what to call. I'm getting kind of buried here, but so far I'm not hitting any errors. So this is why I think it's okay. Because the main reason we passed is we made, right? So we made an interface that has print, and now we made it so that we made a function that only takes printer as a thing. Actually, we made uses printer, so p printer, so that takes any printer, anything that fulfills a printer interface. It's working. I think it's working. I think I'm just overthinking this. I do this all the time. But here's the thing, we didn't return anything from it, and we haven't tested the return values yet. I think I'm doing the thing where I do, and I'm just overthinking it, because I think it's fine. The only way for us to know for sure would be to make an entirely new node implementation, right? The thing that trips me up, actually, no, I think we missed something here. Damn it. So I'm gonna have to go to bed. I'm getting too tired. So this is what is driving me crazy. So when we do this here, add child, I don't think this should be node. Not really. You could use it to be a child interface. Honestly, I think that this is supposed to be, I think that this is supposed to be, because like we don't have this here, right? Print another user use printer, right? And it does p.print. Why? Because it's guaranteed to fulfill the interface. We actually proved the opposite of what we're doing. So what we should be doing here is saying that this is a node, and that's going to break all kinds of stuff, because it's immediately not going to know about node. That means that everything in here, the only thing I can use inside of here is going to be, and anything that's in here, the only thing that can be used in here is stuff that knows about it, right? So anytime I do ch.parent, can't do it. And so this is what sucked me into the vortex last time, because when you do this, you actually also have to add, you can't have it both ways, right? So this is what I'm having a problem with. You can't just have a parent that can be read and that implements it internally. Not if you want to pass it right? So if I want my add child to take in a node, it has to accept a node. The whole point of this is it's going to accept any node, not just a node like me. It has to accept any node. And that means that we've already hit a problem because I cannot change the parent. It also means that all of this, the end.last stuff I can do, right? But this last thing equals ch. What do you think? You think I got that wrong? I think that this is a problem. It has to be a child. Right. So what I'm thinking is I actually, in order to do this, I have to make the parent settable if I'm going to do this way. And I'm going to do add child like this. Yeah, because otherwise there's no care. Yeah, who knows? I mean, I have to make it so I can set the parent. I have to. I absolutely have to. It has to be created to have a parent, and it has to be created to be able to set the parent. So that's the difference. We have to do this. And I didn't want to do this. I thought we were going to be able to get away with this, but we're not. If we're going to keep track of the parent, right, then we have to do that. Then it has to be a child, right? Well, it is a child. It's already a child. Now, the thing of it is we could actually get rid of the parent reference completely. Yeah. Well, yeah, I know, but we can still, I mean, the parent reference isn't a problem if you're okay telling things what their parents are. Yeah. It's a tree. If you're talking about it being a graph, then yeah. Yeah. No, because all of the children need to know their parents. I mean, the children need to know their parents. They do. Yeah. It's not a tree though. You're right, because you would never go up. This all came about because I wanted to be able to go up in the tree. And I think the fact of the matter is we don't actually want to go up. All we really want to know about is who are my siblings and who are my children. That's it. I don't care about my parent. If you care about your parent, then, yeah, no, you can have a return reference to your parent. You can. Yep. Yeah, you actually can have a return reference to your parent. The thing I'm thinking is that we need to make it so that you can actually set it. Coding Rob, if you care about your parents, I know. Yeah, I don't know. It is a graph, but it's also a rooted node tree. I mean, like if you look at the this stuff inside, I'm trying to find an example. If you look at the stuff inside of a web page, right? So so we'll go back to the web page. Oh boy, sorry for that. That's not what I wanted. Page spec info. Where is it? Spec element. To be a tree, it has to start somewhere. That's why we refer to it as a tree. Yeah, but it doesn't mean you can't go up the tree. You can. Some of these things are trees, and you can go up in them. So, for example, and I don't know if I want to. If that makes it's not a tree, I'll call it something else. Because it's more about the functionality. That's what I want to be able to do. And so all of these, this is the document object model, which is definitely a tree. And if you go through it and you can see, look for the nodes, right? Child element, child nodes. So its child nodes are a node list. Now, this thing I find interesting. How's it going? Yeah, we're making videos, but it's a long video. So this node list is a list that's included inside of this of this thing here. Now, this is where we kind of diverge in opinions on how to manage the node, because I don't want to maintain an array, a list in each object. I don't want to do that because it's too painful. I mean, it might be in this particular case, they have caching requirements and stuff like that, but it's a pain in the butt to keep that thing updated such that it's concurrent. Whereas if you just have references to your neighbors, those things are atomic and can just be deleted and changed. Even if it means we have to open up the interface a little bit. So for example, if we have child nodes here, right? And, but what you see here, you see the children, right? But any one of these child nodes also knows its parent. And so they also have children, right? So this is an empty child list node, doesn't have anything in it. But see, it tells you what the first child is, and it tells you the last child. And that's for all the same reasons that we talked about doing. That's why you need that. It tells you the next sibling and the previous sibling. And we have that. In this case, it doesn't tell you the previous sibling, but probably should. And the node name and all this stuff. These are all the values that are associated with the struct that we have, the equivalent. And it tells you the parent element. So the parent node right here, this is a return reference up the tree, right? And so you can get to all that information. And the problem we're having here is that we are trying to make it into an interface versus a struct. And I believe in doing that for all the right reasons, but the more we get into codifying relationships in the interface, the less flexibility there would be in the underlying structure anyway to do things. Now, we don't care how this is implemented, but you know, the hard part here is, so add child, right? If I make add child a node, then I'm going to have to make it so that I can set and change the previous and all the children and everything, because it's being passed in as a watch. So in order for me to get my test to work again, it says too many arguments to call chparent, right? So if I do, so this is what's up. I'm going to have to put accessors. I was hoping to not have to do this, but I'm going to have to now do it. So I'm going to have to say set parent node. All right. And I might have to just accept that this is just life. And then down here, instead of anything that I need to have this, again, pass references, right? So this accepts an interface, and we do set parent. So the child set parent to the current node, which guaranteed to fulfill the interface. And that should get us by a while. So connect use, see, and this is where the whole fucking thing unravels. This is where it all unravels. And because now you cannot use type N as a type node in each set parent. Node does not implement node. Wrong type for child first method, right? Because why? Because the child first method is now returning a node, right? So, and we're going to be doing that. So this is where it kind of unravels. See, it's returning a node, but you remember that whole thing about returning values and not returning nodes? Node does not implement node. Wrong type for child first method. So now the whole interface thing unravels, because these guys, now all of these, they have to, instead of returning a struct, they now have to return nodes in order to fulfill the interface. Yep. And that's what I was trying to get at. So if you put node here, I mean, and then the really bad thing about this is, as soon as you start doing this, you lose the flexibility to do other things to it, because you don't have any insight into it anymore, because you have to cast it. And as soon as you start to cast it, then you've blown out the whole point of doing the interface in the first place. So this has been something that I've struggled with for a long time, and I still need to ask about it. So, you know, this stuff, if we're gonna implement all of these properly, then we need to do this. If you put specific structures there, you've defeated the whole purpose of it in the first place. So we have to do this, right? And now all of our stuff comes unleashed. It all comes undone. Because why? Because here I'm making a collections of these things, right? And now when I'm returning them, I'm gonna have to cast them in order to get them to match. So one at a time, I'm gonna be fixing shit for all night for this. But it's probably a good thing for me to go out on. So this one here, node, it says parent cannot use end up parent as type node and return argument. Node does not implement node missing the delete method. So this is what we were talking about though. We wanted to have it like trigger all these things that it's missing. Catching it, but I think, yeah. So it's missing all of these methods, but we wanted that because then we wanted to say, hey, you don't fulfill the whole thing, right? So let's actually, that's what I was expecting is, and it wasn't doing it at first. And I think that was the reason because we were just dealing with the struct. So, so now, hope node isn't node. Why? Like actual node? No, it's, yeah. So it's just the node. No, it's not. It's actually the word node before, before everybody did that. Can it use parent because it's missing the delete method? I think we already fixed that. Yeah. So what do we got now? It's missing the set parent method. All right. Well, it's got set parent now. So now I'm going to have to do this is what you want. This is it's a double-edged sword because it's also telling you it's also telling you that you're not fulfilling the interface. You need some help from the compiler to tell you, hey, you haven't fulfilled this interface yet, right? And by just passing around the struct stuff, it's not doing it. So you have to actually try to match the interface. Wrong type for set parent, right? So set parent should be node, and then we're going to make n dot parent equals node equals n dot node. I don't know if we're going to do that. We say, I don't know. We could say nd, how about that? Nd equals nd. And so on. Who watches this? No one. I'm just me. So cannot use set as nd node in assignment type, need a type assertion. So now we have to like get crazy, right? So, and this is one of the things where I cannot deal. I feel like I need to put this here, but that would be wrong, right? So we know that's wrong. So now I need a type assertion. So nd parent is an internal node, right? So I don't know. This is where it gets crazy. So then this I have to make this a node. But see that seems like it violates everything to me. You know, how do I know that the node being passed in is going to fulfill that? I don't know that. So forcing it into a node like that, I feel like is going to break everything. Anywhere. Okay, it implements the first. Yeah. So here's the problem I'm having right now, right? So, if we're going to do this right, then this stuff actually has to be like this. Parent is defined as node. So I cannot force, you know, the whole point of using an internal reference is because I want to be able to do magic to the internal reference that the thing coming in doesn't know. But if I set the parent to a node, that means the only thing I can trust that incoming thing to do is what's defined in the interface, which means I should never refer to it in any other way except for as a node, like an interface. And this gets me every fucking time because, you know, it's hard. It's hard. I'm not going to lie. You cannot convert CHS type node into type node. So yeah, there's going to be a ton of this, right? So then the real question is do we even want a node? We have a node struct, right? So this is a pointer to a node. It's got all these other things in it. And you know, it's fine. So previous, end up previous a node. We're going to get a lot of things. So children node here. We're going to have to fix some stuff. Can't convert CHS type node into type node. Line 44. Set if first equals nil. Return node CHS. Oh, wait. Right. So this is tough right here, right? Because I'm just using interfaces again. Return, I don't need to do that anymore. I can just return CHS. Yep. So, yep. But then these things down here, so current.next, yeah, I guess I can still do that. Current.next undefined. Type node has no filter method next, but does have capital next. See what I'm saying? So now I have to do calls for everything. And this is what I didn't want to do. I didn't want to force the internal code that I'm writing to use the interface. And I'm fucked because now I have to do it. And I think this is the way to do it. I just don't want to do it this way. So it's the point of the interface in the first place. I know. The point of the interface is so that other people can implement an interface as well. That's the main point. So that anything that fulfills the node tree interface, which means that somebody might have different types and kinds. You know what I mean? But again, at that point, I'm like, why don't I just... This is... I'm about to throw the interface out the fucking door. I am. Because this doesn't make any sense to me anymore. Because what is the reason for having an interface in the first place? Right? So the whole point of the interface is to say, if you want to implement one of these, you have to do it this way. And here's going to be your methods and everything, right? So it's compatible. What I wanted to be able to do is I want to be able to give other people the opportunity to implement this stuff with internals about, like searching through children and stuff. That's totally up to them. So like, for example, searching through children, if they want to maintain an internal cache that keeps track of all the children, fine. Do you know what I mean? Define what I say. What are you talking about? Yeah. So this is the main reason that this is here. When people add children stuff, I want them to be able to internally maintain it however they want, but we're already getting into the guts of how that can be done, right? So, like iterating over the first and the second to get all the children. Somebody else might implement that entirely different. Somebody else might implement that as they keep a cache of all the children and then they return that instead. So I think having an interface is still worth it, even though it's a pain. So they'll never have a parent. If it's just going to be a search engine to look to use nodes. No. It's always going to have a parent. What are you talking about? This is just one node in the tree, dude. There's like all the other nodes are going to have parents. The top node is the root node, and then we can put in a thing that says, "Are you the root?" You say, "Yeah," because you don't have a parent. Your parent equals nil, right? So then we can do next here, and I'm glad this is captured, but this is like annoying. So this is a case where, so this children method right here, function, whatever, is a real solid example of why I'm using an interface. Because some people are going to want to pre-cache the list of children internally, and they're going to want to fetch that and turn that out first. And so they're going to have different internal logic going on, but they're still going to be calling first and next to get that stuff. But they might not do that, right? So instead of doing first and next, maybe they maintain when the query for children, maybe they don't even go for first and last. Maybe they just maintain an internal cache that's not invisible, and then they return that internal cache, right? So somebody else might choose to implement children differently than I did. Mine is just going to get it every time. And so I still think that there's a value to having interfaces here. I do. It's just not as pronounced. You would interface the child for the tree, interface something else that navigates through the graph. Yeah, well, we're doing that already. So, and that's going to be walk. So, and walk has got to have visibility into all the pieces at any moment because it's got to be able to see where it is and stuff. Yeah, I'm going to interface the children for the tree. Yep. So, yeah, this will be fine. We're just gonna have to say the thing I hate is we're gonna have to make it so they can set the previous and next. I hope I can get away without allowing them to do that. I really do. I don't want that to be a thing. Apparently, the parent has to be allowable to be set. Now, you know what? It's going to break. I know it's going to break. You know why? Because when you make a new node, see, this is the part I don't understand. It's like, this is returning a node, but do we want it to return? No, that's fine. That's fine. That's fine. I need to go to bed. That you can have the growth where it comes from, where it goes to. Yeah. So let's go back. End up first undefined method first, but does have first 46. Yeah. It can be a lot of this for a while. Just give me a second here. Did I save that? Oh, this right here. And so first, current, next, 43. I just saved that. No, it has no field or method first, but it does have a first. And not first is undefined. Oh, see, I hate that has to be a function call now. That just really upsets me. Yeah. I don't know. I mean, this is the part where I'm like, I don't know if I care to have extensibility at all. It's like, just make another fucking structure and then go for that. If you want to have a different one, use your own. I'm seriously tempted to just make this all a struct. I hate function calls just in the middle of my structure like this. I hate it. Is it going to make my node tree more brittle? Yes, it totally is. I mean, again, why do I have an interface? And then I hear stuff on the podcast and stuff about premature, interface definitions and stuff. And I'm like, I don't know if you need an interface for everything. But then how are people going to set anything, right? So, yeah. I don't know. Know what? No, you don't want the interface. Yeah, because if we did an interface here, this drives me nuts. This line right here, like fetching the first and seeing if it's empty before giving a thing. I hate doing that. But you absolutely have to do that if you're going to allow anything to implement your anything to be one, anything to be a node tree. And not necessarily even a node tree, to be just a collection of associated graphs, I guess. Not really a tree at that point, right? It'd be a collection of graphs. I mean, this will totally work, and it'll be fast. It's just not going to be. I don't know. I'm like right on the cusp of like throwing it out. This thing here too. I think you has a variable node passed. No, you absolutely can't. Because that would be giving this internal knowledge of what it is, and that would be a cast, and you're not doing that. The whole point of using the interface is hiding the internals of the thing that's coming into you, even if it's your own thing. And that's what's got. Oh, you absolutely do. You absolutely do. I know you do. If I do end out first here, it doesn't know that's. Oh, this one might not need it. Let's try. Yeah, I think you're right. That one didn't need it. So that one didn't, thank God. This one definitely will need it though. Because we need to look up the current, and the current is the next. Do we need to do that? Maybe we don't need to here. Something else is going to blow up here, I have a feeling. We just need, yeah, because, here's why. Because we need to return a bunch of nodes that fulfill the interface. Yep. And, yeah. I probably need a cast there, a special cast there, and this is where I'm getting kind of hung up. Has a filter method next, but does have next. So we could do, wait, see that current? No. Because we changed next to be nodes. See this? No, this is not going to work. I'm getting tired. This is pissing me off. I got to tell you, this is one of the things that is the hardest for me to get my head around and go. And for everybody struggles with this. Everybody. I know people have been coding Go forever and they still have trouble with this. When do I make an interface? And then you hear about people who have like 10,000 people interface. This cannot be a node because at some point we're going to have to cast it if we're going to do that. Yep. Because look, we're going to have to go down here and we're going to have to say, we add a child for node there. So this has to be that way. And if we're going to iterate through it, yeah, on line 6046. So if we're going to return a list of nodes, which we're required to do by the interface, see, this is where I really, really want to be able to return just an array of nodes, but you can't do that. That whole shit about returning a specific thing, I don't buy it anymore. Because how do you define an interface that returns a specific member of another interface? You can't do that. So you have to define it this way, and otherwise they don't fulfill the interface, period. So that means I'm going to have to do some casting here going on the way out, which is fine. That means that if I'm going to do an internal, no, I can't do that because these are already defined to be nodes here. Yep. And if the incoming thing is a node, yeah, I can't be sure I'm ever going to have, yeah, so that has to stay that way. And then, yeah, that's it. You don't think I need to make a call? You can't access the variable in the node past. No, you absolutely can't. What are we talking about? No. Because if you do that, you're violating the whole point of the interface in the first place. So yeah. And it's easy to do. The first time I did this, so I did this last summer. The first time I did this, I actually cast a bunch of incoming interfaces as the internal type. And then that breaks the ability for anybody else to use a different implementation of your interface. Because now you're trusting this thing coming in and you're forcing it to be exactly like all the rest of your internal stuff. And that's completely against the point of the interface. And it's annoying. It's really annoying. So current.next undefined type node. I gotta go to bed. I'm getting pissed. So current.next undefined type node has no filter method next, but does have next. Okay. So line 46. So these I think I can get away with. No, I can't because I'm gonna have to do the call. Yep, I'm gonna have to do calls for all of this. I really don't want to do that. The only other way to do this would be to expose. You know what? That's the way to do this. Wait. No, because then it wouldn't be part of the interface either. You can't. Yeah. It is a node. Yeah, it is. And I know. First. So that is a node, so that's good. Current, and then current dot next. So that does have to be uppercase, yeah. In the interface. So this is the internal first, and the current equals nil, and the current equals the current dot next, and that's gonna give us the next one. That should actually work. That should totally work. Undefined last dot next, yeah. So this is a different thing. Hey, that got us past that problem, so we're good. That's good. Yep. Okay, so we're back to add child now. All right, so add child node, we need this. Set parent, if we're gonna have a parent relationship, we have to have that. We could drop the parent completely. Instruct, yeah, no, it doesn't. X is right here. Yep. So that's fine, but you can't use it. You can't use next because you want the next of the incoming node. That's what you want, unfortunately. So I mean this will work, but yeah, because we want the interface. We can't trust the internal infrastructure of that. No. Anyway, so we got a node, new node. That Marshall's node FMP and string. Okay, that's fine. Add child. So this is a thing. End at last is not equal nil. Okay, so end at last dot next. So this actually we have to call because it's no, we don't. Last, yes we do. Yeah. I mean, it unravels, dude. Because if what I want to do is I want to go back to changing these to be pointers again. As soon as I change those to be pointers, all of this breaks. This all breaks because, I mean, let's see. The incoming stuff can't be set without casting it, in which case I'm assuming all kinds of stuff about it. And the outgoing stuff is fine because the internal stuff is this could cast it because it's outbound and I'm guaranteed that it fulfills it. But this is where the problem is being able to change values because, yeah, we're going to have set next and previous too. I almost guarantee it. Cannot assign. Yeah, that's what I was just going to say. So there's I knew it was coming. I knew it was coming. So we cannot have this. So this means we have to do a set next, which means as soon as you have a set next and that shit, now you've just exposed everything that you were trying to protect yourself against, right? Because now it's a part of the interface. And so now it's like, what the fuck do I have an interface? Because as soon as I do this, as soon as I do set next node, right? Honestly, why am I even bothering with the insert before and all this nice safe add child stuff that's supposed to be hiding us? It's supposed to be hiding the user from all the details of organizing their own node tree, right? And at that point, I just throw my hands in the air and I'm like, no, I'm going to make the whole fucking thing a struct. And if you want to play in my world, you play with my struct, the end. And that's what I'm going to do tomorrow. I'm going to throw out the interface because I think the interface is flawed. I think it's flawed. The whole point of the interface, I'm going to throw it out because I don't need it. I don't need the interface for this. And if you look at all the internals from the Go stuff, it does not use interfaces for node trees. And in fact, it's kind of silly to use an interface for node tree. Why the mix of a struct and interface are we talking about? The point of having a thing that implements it is so that you can do stuff with it. But the problem is that there is so much internal stuff in what we're talking about here that you cannot have it be an interface. You can't. In fact, I would if anybody can actually find an implementation of an interface node tree. I would be super surprised to hear that, because I feel like node trees and nodes are extensions of types. There's no such thing. Okay, so yeah, this is going away. You're dead. Minimizing themselves. Yeah, the interface is unnecessary. I don't think it's necessary. I want to start thinking more like a C coder in here, right? So then I'm going to have a node. And the other thing too, now I can actually use zero values. Yeah. So, if I truly want to make something that's reusable, I just uncouple this whole entire thing from everything else, and then I let everybody play with it however they want, and then I suggest, this is much more idiomatic Go. Why are the O's highlighted? Oh, just because I picked them, that's all. So this is much more idiomatic Go. Idiomatic Go says allow everything to be public and let people use stuff, and then if they want to fuck it up, that's fine. But if you don't, you can go ahead and just make it all that way. So you have the parent, have the previous, have the next, have the child first and child last, and that's it, and that's all I'm going to expose. So another thing about this too is that this is immediately serializable. I can serialize this like that because it's a struct. I can't do it with an interface. So I'm kind of happy I'm going back to this. I feel bad that I went through all this hassle. I'll probably just delete this whole video. It is cleaner, but it's also much more rigid, and it's way faster because there's no indirection, right? So, and I don't need any of this shit. Any of this. This is all gone. Looks much like C. It is C. It's simplified C. And I got to stop thinking about Go as Java. I do it all the time. I've coded enough Java to get totally corrupted by that. Strager's coming over with 72 just to see me rip the crap out of my interface. Strager would probably really laugh at that. Why not to do things right? Well, I want people to see, you know what? I'm going to leave it. I'm going to leave it because I want people to see that sometimes, yeah. Oh gosh, that's so nice. Strager's great too. So Strager, I just spent the whole night, making a nice, pretty interface and realizing I am like totally doing it wrong. You came for the fish, Darth Vader. Seriously, I'm like, what are you even thinking about? Why would you do that? So I try to make, I mean, it's a nice, pretty interface, right? And then I'm like, rip the crap out of my interface. I was like, no, just give me a node tree. I'm going to export all my fills. I don't give a shit. If you want to play around with the node yourself, if you sincerely think that you are good enough to start messing with all the references in your node tree, this is what we're building, by the way. What font is that? Which one? This, oh God, I don't know. I think it's Ubuntu Nerd Mono, if I remember right. Big on the raid experience. No, it's fine. I like the raid. Thanks for the raid, Trigger. Can we walk the tree now? We're not ready to walk the tree yet. We can. Oh, we're gonna walk the tree tomorrow, probably. Not tomorrow, probably next week, actually, because I got stuff. That is, if I'm going to keep doing what I've been doing. Honestly, I don't know if I'm going to be able to keep doing it. So just in case, I'll tell the raiders, this is what we've been doing all night. I built interfaces to be a toolbox to deal with classes. Yeah. I'm doing some graph theory right now. Are you really? Awesome. This is a rooted node tree. So, and the reason I'm doing it is because of something I've got, you know, motivation here. I'm scratching an itch to get my pagan stuff back. I have a thing called command box, and I have command box doc. And so this is pagan.dev. I mean, just to catch you up so you know what's going on. So Pagan is parsing expression grammar from Brian Ford. It's a notation. It's a meta language that I wrote that extends PEG, that combines ABNF and EBNF with PEG. for things like, like limits, we don't have, Peg doesn't have any limits, doesn't have any, but it brings like recursive descent sort of parsing approaches. It's got left to right priority, unlike eBNF and some of the other context-free grammars and stuff. Well, so the big thing that my big bring to the table here is that I wanted to make a meta language that actually kind of assumes an AST to begin with, so that you can, so here's the long form AST that comes out of a grammar, right? So you parse a document. This grammar here is, this AST is the AST of Peggin itself. And so I've done all this before, but I've just been wanting to factor out the tree part of it and make it available for other things I'm doing. And so we have a grammar, and then you either, is have really, really simple nodes. You either have a value or you have children. You don't have both. Or attributes, no attributes. And I like that. It makes it nice and clean, easy to parse. Short form has just an integer here, so it's even smaller. It's more condensed. It's not pretty printed or anything. So there's a short form and there's a long form. Okay, so that's an AST. And so, I've been playing around with some of the stuff, and I've just been rebuilding my node tree. And actually, I was tempted. I played around with generics. You guys played around with Golang generics at all? So I did. I started a generic Docker container. And so here's my generics. I'm going to sample. And I have main.go2 here. And so I was just playing around. You don't get syntax highlighting because go2, that's actually not. It's just generics. Yeah, and so here's how you do generics. One of the reasons that I'm revisiting the node tree that I already wrote and the parser and everything is because I'm trying to see if generics are going to impact it at all. And they actually are if I wanted to. So one of the things generics would be to bring to the table is if I knew, so my nodes in my tree have a type, it's an integer, and they have a value. And right now the value is an interface. And an interface type, an empty interface type in Go is anything. And you just have to, at runtime, you have to type it. Actually not at runtime because it turns out to be compile time, but it has to type it and then give it, you can pass anything. It's really nice for this kind of thing. But if I knew in advance what type of node I was going to have, I could set the type for the value, and then I could force my node tree to be all, homogeneous types. I could have a node tree of strings only, right? And I could do this. I was thinking it was going to give me more of that. I was thinking it was going to give me more flexibility in terms of what the value would be, right? So I could isolate the different types of values or something. And I don't think that's the thing. In fact, something that's really annoying about generics is if you, so here I made a type called number. This is the new in Go. This part might look familiar to a Go programmer, but this part down here certainly is not. Being able to define a type like this, there's a lot of people up in arms about this, by the way, because the type keyword does not mean what you thought it meant. It's like that quote. It's because now the type keyword, if you put it within a type definition of an interface, it says, hey, this type is actually a composite of all these other types. So it can be any of those types. Any of those types are good to go. And then you use that type down here and you're like, okay, a number is any of these specific types, right? That's something you could not do with empty interfaces before. You'd have to have checked it down below. But the problem with it is if you try to use the old way and the new way, right? If you try to use the new way or the old way, which is, like type switching, which is what this is doing, then you actually have to cast the thing as an interface in order to get its type, even if it's one of these types that you already knew about when you declared it to be a number. So that is some convoluted shit. And I'm not sure that I'm writing it in the best way here, but I'll tell you right now, generics are going to complicate Go to the point where people are going to be like, what? And it kind of pisses me off. I mean, I was okay. I'm not the only one who has this opinion, and more people are coming up with this opinion. At first I was like, okay, it's going to get us new things. One of the things I thought it was going to get us was this nice, cool, node, some ability, map, filter, reduce. That's one of the things it brings to the table because, you can actually pass, you don't care about the types being passed to it. When you instantiate interfaces, select one of the types in the implementation. Yes, it does. And so So yeah, so this would actually be redundant. This code would never be useful because you're right, because this would always return one of these values once you instantiated the function. You're right. Yeah, absolutely right. Okay. Yeah. Thanks for that. That's a good reminder. Absolutely. Because here's the instantiation. By the way, I got really creative here. Like, yeah, when you instantiate it would only be one. Yeah. Anyway, so that's generics. One of the reasons I'm revisiting the whole tree thing, and just went down this like real rabbit hole of like using interfaces where I really didn't need one. I should just stuck with a struct all along and let people do it. That's what I'm going back to. So I'm going to actually publicize the node. I'm actually going to drop all my constructors. We don't need them. This is all gone. And add child, I'm going to keep these because there's a bunch of stuff that has to be done to make that happen. And yeah, they are kind of a blueprint, but they can also get in the way too. So previous node, next node, the parent node, the first child node. Should we do child first or first child? So we should do first child. First child, how about that? Last child, I don't care. It just reads nicer. First child node, the last child node, the next node, the previous node's parent node value, and that's it. That's it. That's all you get. And this can all be JSONed or YAMLed. So that's all good. And then the children, I'm actually going to fix all this stuff right now. Searching for this. I can probably fix this and get it to go again. And you can see what's up. The pointer to a node. And yeah. First node and last node. No, it's not that though. It's a sub node, dude. Previous sibling, next sibling. I at one point I threw them out and just said first and last. Because I'm actually going to keep that. I want that. I don't care. So first and last. So this is the first child, the last child. But see, you don't know whether it's a sibling or a child. Yep. You can't say first node because you don't know which one it is. Right? So we should probably do this. I mean, if we really are going to be good boys and girls, we should really do this. Because that's what it is. Previous sibling, next sibling, first child, last child. Because we got two dimensions going on, right? Parent could be the starter. Yeah. So you got a parent, previous sib, next sib, first child. No. I think you're trying to recurse, like descent, and we're not doing that, right? So root, parent, right? First child, last child. I think you're trying to do this. And so this is your first, and this is to be your second and next, and that's not. So I'm trying to do that linear kind of thing. So root is a parent, right? So, yeah, I'm gonna fix all this before I go to bed. This is not gonna take that long. So a bunch of node pointers, I can fix this. I can fix it. First, child, current dot, next. I don't like next sib. Fuck that. Previous to next can just be like a list. First child and last child. That's the distinction. All right, so that's good. Actually, that's not a function call anymore. Thank God. Thank God. That was when I knew we were going astray. I knew we were going astray when that was the thing. Add a child. We want to add a new node pointer. This is capital now. Alrighty. So we don't have the parent anymore. So we can do this. We can say n dot parent equals, no, we do ch dot parent, right? Parent equals n. There we go. N dot last equals nil. Last dot next. I like it so much better already. Previous, last, N dot last. So this all stays. First and last. Actually, this is first child. I think I'm going to have to keep that on there. Because it, yeah. So the next one of the last child, the one that comes after that equals that. This works. Makes it readable too. Nice. All right. So we're almost done. That was it. Can you believe that was it? Yeah. So let's go revise our test here. Oh, I already did that. I'm in the wrong thing here. All right. So, oh boy, I got two things open. Bad me. VI tree. I should also know that is the comparison is to last. Yeah. Did I do it wrong? What did I get wrong? Did I get something wrong? First, oh, this is this gets changed. This is first child. Child. Equal nil. Next current. Blah, blah, blah. Node pointers. Add child. Super easy. Current equals n. Last child. It's not equal nil. Last child. Last child. Last child. First child. All right. So let's do our testing. Undefined tree.new node. Yeah, we killed it. Bite me. Where did you see it? This? Press the last. I didn't see it. So we're gonna do this. I'm so happy about this. So now I can do this. I can do new tree.node because I am doing the go away. The end. Actually, I can even do one better. I can do one better. I can do this. I can do it equals a tree.node. And oh my God, what did I just do? I set the kind and the value. Yeah, at the same time. I am so happy. You know what? Nodes are structures. They are. Why was I so confused by that? I should never have done that. I should never have done that. I need a fucking constructor for this. I've sworn too much. There's no way this is going to stay on YouTube very long. God damn it. Look at how much better this is. I mean, seriously, people. Tree.node is an other. And my linter would yell at me because I'm doing ordered priority stuff, but I don't care. This is beautiful. Beautiful. Out of the depths of pain and suffering comes the beautifulest code. All right, so then we're going to add all those children. Add children. What if we did add children and then we even did better? Yeah, I'm going to do that right now. I'm going to add children. Add children. And now we get a variadic. Yes, we do. For the chitlins. Did you said R? I don't know. Children. You know what? I'm gonna just say add. I am, because I am just off. I am just off my rocker right now. I'm like redoing all kinds of stuff. I mean, look at how beautiful that is. For child in, how about this? For CH, nope. For CH, add can be variadic. It totally is, yeah. You like that, right? I thought you liked that. Again, this is high level stuff, right? So, yeah, we'll make it variadic. And so say add for equals range. You know what? All that yelling has made me happy now. And put this all in here, and we'll be good to go. So we're not going to have a return there. So for each range of the children, set parent. Actually, you know what? You know what I'm going to do? Yeah, I'm lazy. This is just being lazy. I'm sorry. I'm sorry. I'm just being lazy. I know it's an indirection and stuff, but you know what that means I can do now, right? So I could just do for child close range children add. I mean, it's probably going to get inline, so I'm not going to overthink it. It's kind of beautiful, actually. N dot add, and we'll add just the one child. How's that? Does that make everybody happy? And there we go. So now I could do r dot add COL 2 and new first. What was it? Okay, so new tree node. All right, fine, so be it. New first, let's choose a 3 and first. I like that my nodes can be compact as long as my editor doesn't scream at me in my Vimgo. Linters hate that. I told you already, right? I can even put this all on the same sort of line there. And we're actually not doing anything with that yet. So I will do something later. I'm not going to do something now. Oh boy. And so all of this code's got to change. So what kind is it? What's its value? What's its parent? Don't need any of that, any of that, any of that. Hey, how's it going? And then we don't need this. Previous. Oh my God. Look at, I'm losing all these parentheses. It makes me so happy. This is the way to go. I feel so much happier. I love structs. I'm just going to say it. I love structs. I am a C coder at heart, I think. It's better, huh, for him. So it's much better, right? Much better. Much, much better. I was getting off in interface land and I need to go back to, I need to get closer to C unless close to other stuff. Children is a call. Now, I could easily keep children updated, but I can't always be guaranteed that that's going to happen, right? So if people add, if they do add with that, I could actually have a cache of the children and just go through that. I might do that eventually. That's a very C thing to do, but right now we're just fetching it. I don't know. I mean, if I had something delete itself, I could say delete myself from the parent, and no, not want to do that. I'm going to have slice use children. First child value. What's the first child value? First child, last child. I still think we need to keep child in there. First child value, child last child. And how are we doing? Undefined ch kidoki. Oh right. We call that a child now. I'm gonna change it from child to ch again. Why the fuck not? Just put child there. I mean, it's not that much more. And what's up here? The children's. I'm going to make a children. I'm feeling gregarious. It's not that much. This is not as bad as C++ or something. Child, add a child. All right. Too few values for tree.node. Are you going to make me do them all? Fuck that. Fuck that. Okay, fine. I'll do this then. It's a better way to do it anyway. And there I said it. You do like Sage and N. Well, let me rethink that. I mean, yeah, it is a little bit dirtier, isn't it? What if we just did C? What about that? This is very gooey. This is gooey. See, that it puts the focus on the other stuff. All right, I'm with you. I'm with you on that. Look at how clean that is. Oh my God. I'm with you on that. Now, children, we have to kind of have that though, don't we? Yeah. Party of 8. What's up with these raids? I'm never going to go to bed. So we're just adding all the children's. That one's fine. So add adds the children sequentially. The end. So I don't know what to say. As I go on bytecode. So I'm gonna have to. This is actually a bad form. Your linter will yell at you. So I'm gonna actually have to change this. So this is a kind. This is a kind. I don't want to do this, but oh well. It's either that or I have to define all of the variables because it doesn't just take the first ones. So this is a value. Value. This is a fast way to do that. I could do this separately, and that would be fine too. But okie dokie. Wait. Uh-oh. I screwed up. 2 test. Tree.new node. You don't exist anymore, so bye-bye. There is no such thing. There is no new node. There is only Zool. So new node can go away. Yeah, what's this? Daff that function. And now we just have a node. The end. One example test. This isn't even that hard. I don't even know why I overthought that. I'm such an overthinker. And you know what? It's dangerous. Overthinkers like me, we can be good and we can be really bad. I mean, I end up making really high quality software because I overthink it and I spend a lot of time thinking about what I'm going to end up making. But I also overthink it to death. And so then I go back and forth like 10 times. I've struggled with my whole life. I have. And I don't think I'm the only one. I think there's a lot of employees at Google who do the same thing. So I wish they would overthink some things a little bit more. Perfectionism. Yeah. So tree node 1 var nil. Look at that. And then we have bar nil. Did we do something wrong? No, that's the config should be right. Other foo bar last. Last foo other nil. Free children bar last fail. Why are we failing? Root child other last. Root child other last. Tree node. Oh, because it's not it's uppercase now. Yes, sirree, Bob. So we have a tree node. You know what? I didn't even need that anymore. I don't even need that first field because it's public. Yep. I can delete it. So you're gone and you are gone. But delete capital words. There we go. Did I do that right? I think I wanted something else. I will. D word. I'm lazy. All right. Pass. Yay. All right. Well, that's it. I'm going to go to bed. 1 o'clock. Thanks for the raid, bytecode. But who else are we going to go raid? Should we go raid somebody? You know what? I'll put some music on for you. You guys want to watch the music? Listen to the music. I'm going to drop the stream, though, because I need to make sure this video gets to the right people and that they watch all the way to the end. I'm going to suggest, hey, jump to the end where he gives up all the interface. That's the most exciting part of the whole thing. Yeah, I need to wake up tomorrow morning too. I got lots to do. And so yeah, then we have a node tree. We've implemented pretty much everything. We need to do some insert before and other stuff like that, but for the most part, we have a working, a working system of nodes, and it's going to enable me to do a bunch of other stuff so I can do some parsing. But here's the test to prove that it worked. I love that so much better. It's so much cleaner, so much simpler. All right, that's all. Bye.